I'm being told that. Oh, so am I audible, Saurabh?
Yes, you are
Yes.
audible.
Okay. So, as I'm being told that the last session exceeded its time and we are still waiting, I think there will be a delay maybe for 5 to 7 minutes to start this session after the lunch break. So, please join us as early as possible. And I would ask the poster presenters to be all ready and all joined here so that uh, whenever your name is called, you should be alert and you should be there to present your poster. So we are waiting for a couple of minutes more to start. Please stay tuned because we are going to start the poster presentation session shortly. Please stay tuned because we are going to start the poster presentation session shortly. Please stay tuned because we are going to start the poster presentation session shortly. If all the judges and all the poster participants are online. So can you please maybe switch on your video just to make sure that all the poster participants and the judges are online.
There are 8 participants are there. So, Ungsuman, you are not participant.
No, fine. I mean, the judges can also please stay tuned because till we are ready to start poster presentation session. If all the judges and all the poster participants are online, so can you please maybe switch on your video just to make sure that all the poster participants and the judges are online.
There are 8 participants are there. So, Ungsuman, you are not participant.
No, fine. I mean, the judges can also please stay tuned because till we are ready to start
if anyone has having the network,
all the judges and all the poster participants are online.
So that we can
So
start.
can you please
Until and unless
maybe switch on
everybody
your
is present,
video
we cannot start. So,
just to make sure that there are 8 participants and the judges are online.
Problem. She messaged that. There are 8 participants are there, so that's why she is there. Ungsuman, you are not participant.
No, fine. I mean, the judges can also please stay tuned because till we are ready to
if anyone has having the network,
judges and all the
you
poster
can tell us.
participants are
So
online.
that we can
So
start.
can you please
Until and unless
maybe switch on
everybody
your
is present,
video
we cannot start. So,
just to make sure that there are 8
girls,
participants
we
and
are in
the
live
judges
in
are
YouTube
online.
channel. So I can share you. There are 8 participants are there, so that's why she is there. Ungsuman, you are not participant.
No, fine. I mean, the judges can also please stay tuned because till we are ready to
If
start
anyone
the
has
presentation
having
session.
the
All
network,
the judges and all the
you
poster
can tell us.
participants are
So
online.
that we can
So
start.
can you please
Until and unless
maybe switch on
everybody
your
is present,
video?
we cannot start.
Okay, so just make sure that there are some participants
Girls, we are in live in YouTube
poster
channel.
participants.
So I can share you. There
Anjit,
are
Jana,
8 participants are there.
Anjit,
So
Shivani
that's
Reddy,
why she is there. Ungsuman, you are not participant.
Suvankar Chakravarti. No, fine. I mean, the judges Tanushree De, please stay tuned because till we are ready to
If anyone
start
has
the
having
presentation.
the
All
network,
the judges and all the
you
poster
can tell us.
participants
So
are online.
that
Joined by
we
now.
can
So
start.
can you please
Until and unless
maybe switch on
everybody
your
is present,
video?
we cannot start.
Okay, so just make sure that there are some
Girls,
participants
we are in live in YouTube
poster
channel.
participants.
So I can share you. There
Anjit,
are
Jana,
8 participants are there.
Anjit,
So
Shivani
that's
Reddy,
why she is there. Ungsuman, you are not participant.
Suvankar Chakravarti. No, fine. I mean, the Tanushree De,
Please
stay
stay
tuned
tuned.
till we are ready to
If
start
anyone
the
has
presentation
having
session.
the
All
network,
the judges and all the
you
poster
can tell us.
participants are
So
online.
that
Joined by
we
now.
can
So
start.
can you please
Until and unless
maybe switch on
everybody
your
is present,
video?
we cannot
Very
start.
sign. So just make sure that there are some
Girls,
participants
we are in live in YouTube channel.
and we are
So I
going
can
to
share.
start
There
the
are 8
presentation
participants are there.
session.
So that's why
Let
she
me
is there.
brief you about
Ungsuman, you are
the
not
games.
participant.
So each of the participants find Tanushree De each.
Please
Please
stay
where
tuned.
they are shares
If anyone has having the network,
and the judges and we asking them questions. So can you please maybe switch on your video? So just make sure that there are some participants
we are in live in YouTube channel.
and we are going to start
There are 8 participants are there. So that's why
and also to mention
Ungsuman, you are not participant.
so is having Tanushree there. Please take over. She shares and explains their views to the and the judges. And we ask you the questions. Can you speak that
We are in live and
we are going to start.
there are 8 participants are there.
And also
I hope you are not judges are present here.
having Tanushree there. Please take over. She shares
Am I audible?
explains their views to the and the judges. And we ask you the questions. Can you speak that
We are in live and there are 8 participants are there. I hope you are not judges are present here.
Am I on the target? Using mass spectrometry studies where the nanomolecule have a characteristic spectrum and characteristic mass peak at 37.11, which is exactly matching with the molecular composition of silver 42 and 15 of that carbon diphenyl ligand and 4 triphenyl phosphine. Go down. Then we have confirmed this nanomolecule using MSMS fragmentation studies where we have selected that particular peak and then we have got G7 and we have mass sequentially increase the collision energy from collision energy 0 to collision energy at 30 fast collision energy 150 to collision energy 1.11. So which is exactly the peaks are coming which are the mass gap of 150 triphenyl phosphine ligand. So by that way out of 4 triphenyl phosphine molecule getting detached from the cluster and sequentially there are carbon using carbon losses is happening when the collision energy where we have 150 to 200. So by that way one comes sequence of this cluster as silver 42 collision energy triphenyl phosphine collision energy and carbon diphenyl collision energy 1.8 to collision energy 200 down 1. So which is exactly the peaks are coming. So then we have characterized this molecule using its structure where you can see that molecule have been allocated silver from the class which is that is true sequentially and that metallic silver 28 core is further protected by this silver atom that is pink atom by the and then you can see one whole triphenyl phosphine cluster that is in green color collision is surrounded in the cluster surface carbon diphenyl and we have confirmed this molecular composition using its vertical optimization feature where the characteristic peak exactly matches with the experimental spectrum molecule and we have observed that this high strength peak that is 472 degrees after from the class which is that is true some number of homos called metal silver where the collision is postulated we have confirmed this cluster by the using TEMC1 and recognized this cluster shows the remarkable in high stability after 1 degrees in the cluster surface carbon diphenyl and we have confirmed this molecular composition using its vertical optimization feature where the characteristic peak exactly matches with the observed this thermally stable silver 42 nanomolecule is highest contrasting to other 7 nanomolecules in presence terms of light, which is a little bit some number of photos and one the corresponding. So we are observing that this silver 42 nanomolecule intelligence of light, even they are converting to silver 14 nanoplasmids. They are just degrading their code from silver 42 to intermediate state of nanoplasmid, that is intermediate energy to make like the intermediate bond is concentrated in silver 37 and silver 35 nanoplasmids. Remaining second intermediate into outer silver and silver intelligence of light, which is that fast to get forward using this optical approach picture where the stages sequence are observing that this silver 42 nanomolecule changes of this light from working one silver intermediate to second intermediate and after integrating silver 14 nanomolecule to convert this intermediate for this intermediate conjugate mass spectrometry where you can see that the intermediate bond is 140 nanoplasmids is converting to some other cluster that is the mass intermediate which is converting to RT7 and RT5 and subsequently it is converting to the fast to get forward using this optical approach which is conversion of this 42 nanomolecule changes of this light from working with single system intermediate to second intermediate. This is the recording silver 14 nanomolecule to convert those light polarization and second and silver polarization where we can see the polarization and see the indicating the distance and we can see the particle cluster converting to it showing that compared to the working heavy silver is converting to RT7 and RT5 inside code and it is converting to the first to get 6 and this is the RT7 is 6% of this corresponding and this molecule molecule changes like this every single system this discovery is compounding the cornerstone converts the light into the second and polarization where we have studied what is the kinetic resistance so we have just started to mathematical studies like the real and transition studies or you can see the real spectrum of silver 42 and silver 14 silver 42 is 6% so it is molecule at 980 nanometers like even silver every just the same distance in a research mostly we getting the cornerstone very narrow energy gap in compared to silver so the narrow energy gap is responsible for this studies to mathematical studies like the real and studies you can see the real spectrum of silver 42 and silver 14 silver 42 is 6% so it is molecule at 980 nanometers like even silver every just the same distance so we have been getting the cornerstone studies even the energy gap in compared to some silver that is silver particle so the narrow energy gap and we have observed that this particle transition at 486 nanometers which is happening in the 4 minus 4 and 4 minus 3 which is average of the corresponding voltage silver to the different loop so silver 5 is 6 so we have on the molecule which is like that silver transition is happening for the synthetic code so we have been getting the molecule studies even the energy gap in quantum dynamics so we have discussed that silver particle so the narrow energy gap and the density of this particle bodies two molecules the other molecule which is happening in the 4 minus 4 and the light and average of the corresponding so fast makes the time to resist so the molecule is showing which is like represented target and happening for the synthetic where you can see that this corresponds to having convergence from starting and even about the in quantum dynamics after we have discussed that silver particle so the narrow energy and the density of this particle bodies and molecules the other down which is happening for the and average of 4 is the light and average of the sound is reaching and we have observed that the fast makes the time to resist so the which is like everybody micrometer is happening for the synthetic where you can see that this corresponds to having even about the quantum dynamics after we have discussed that the core of the narrow energy there only is that start happening for the molecules the other down which is the last and average of 4 is where you can see that they have charged and the light is reaching and we have observed that the molecule has been time to resist so that is indicating that there is more charge which is working everybody micrometer is getting the last where they are passing the due to that radiology power is even about the Mostly, mostly, most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. But in terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. But in terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products. Most important direction to stabilize this area is to test these are proper matrix. Nice in that direction, the people use polymer and some other matrices. In terms of thought absorption, this molecule is nice. As much as you can stabilize them, you will get the solar cell application. Efficiency is stability for this kind of materials. Mostly organizing direction consulting to other products.
different pattern. Then it matches it with the experimental pattern. Now there are two parameters, RP and RWP, residual parameters. They are used to evaluate the matching. The better the match, the lower the RP or RWP values. So it then orients the molecule randomly in the crystal, in the unit cell, and it it works on a trial and error method. So there are almost 10 to the power 7 trials in one run of Fox, and the best structure it gets, that is with the lowest RP or RWP value, it gives us it as a result. So the base structure is then used for refinement, Rietveld refinement, further using the program GSAS. Now the what we did, we got the crystal system to be orthorhombic, and then we have got the ABC, volume, space group, all were correct until we did the refinement. So while we did the refinement, when the refinement converged, we found that there were two peaks which were unindexed in the powder XRD pattern, which we got from the Bruker machine. So there was no explanation of those peaks, because we had tried more than once. A lot of times we had tried, we got the same crystal system, same unit cell parameters, but the two peaks were unindexed and we did not have any explanation. So we went for structure determination with synchrotron data. And surprisingly, the synchrotron data which we had collected with a very small step size, and that is 0.001 degree of step size and the step time of 0.1 second, 1 second per step, with the wavelength of 0.459 angstrom. We got that data and we did the whole process just like earlier, and surprisingly we got the same cell parameters and the same space group, and again there were two unindexed peaks here which could not be explained. So then we did the search match program with EVA, and we found that those two peaks were due to some impurities, and this impurity was nothing but common salt, sodium chloride. So anyhow, it was a purchased product from Sigma Aldrich, but we had some impurity. Then we did the quantitative phase analysis using GSAS. So in quantitative phase analysis, it was found that there was 1.68% of sodium chloride present there in the sample, and it was the reason for those two peaks at around 9 degree and 11 degree in the synchrotron data. Then when we did the quantitative phase analysis, after that the whole refinement converged and gave us very good RP and RWP values. As you can see from the table, that RP value is 0.0523 and RWP is 0.0766. So thus we got the quantitative phase analysis and we got the structure of 6-amino nicotinic acid. Please move it upward.
Okay.
Some more. Okay.
Just a little reminder. So you have extended the time. So please try to wrap it faster.
Okay. Okay. So here we can see that this is the final Rietveld plot, the figure 1, which shows a very good match. Next figure is figure 2, which shows the molecular geometry of the molecular view, and along with it we got we did solid state DFT of the molecule. So this is a matching of the two molecular conformations as obtained from the XRD, the pink one, and as obtained from the DFT is the blue one, and it shows a good match, showing that our structure was correct. Next, we can see that there are various hydrogen bonds present here. Sir, a little bit downward. So there are very strong, some more, the last bit. They will do. Okay. So if we can see that there are NHO and OHN, three types of hydrogen bonds present here, and the HA distance is 1 point of the order of 1.95 angstrom, which shows that these bonds are very strong. And along with this hydrogen bonds, a three-dimensional supramolecular structure is formed. Please go to upward to figure number 3. So figure 3 shows the three-dimensional supramolecular architecture formed by the different hydrogen bonds. And we can show the hydrogen bonds using the Hertzfeld surface also. We had calculated the Hertzfeld surface and fingerprint plots using the crystal explorer, where these red marks denoted by A prime, B prime, they denote very strong contacts. And the same thing is given here in the two-dimensional fingerprint plot as spikes. So here very strong hydrogen bonds are present, and we had also calculated molecular electrostatic potentials using isolated molecule DFT calculation, which shows that the red areas in the MEP surface at figure 5, they show highly negative charge, whereas the blue areas show highly positive charge. So it also goes with our hydrogen bonding calculation. Next, I want to conclude that the structure was very simple, but the problem was the mixture of phases, and we were lucky enough to get the structure because the peaks did not appear in the first 20 peaks, because the first 20 peaks were very important in doing the indexing part. And as there was no problem in doing the indexing part, we got the other two parts, that is structure solution and refinement, quite easily. But if the impurity level was very much higher, then we could not have also got the structure from Fox. So as the impurity level was very small and there was no contribution of impurity in the first 20 peaks, we were able to solve the structure. That's all. Thank you.
Thank you. We are significantly going delayed. So, any questions? Okay, so if we don't have any questions, we'll go to the next presenter. I would like to check again if Manjeet Bora is there. Okay, so if he's not there, we'll go ahead with Pratik Boga.
Yes, I'm here.
Please stick to the time because yeah, it's we are all like almost going double the allotted time. So let's try to stick.
Of course, I understand. Uh, okay. So good afternoon, everyone. This is Pratik Boga. I am a student from Shastra University, and I'm here on behalf of my student colleagues to present our research on dark matter distribution around the spiral galaxies. So from history, we might know that rotation curves was...
Just to interrupt, Pratik, one
course.
particular thing we want to mention. Whatever the questions will be asked by yourself, no teammate can answer.
Of
Fine?
course. Sure. Yeah.
Okay.
Thank you. So as I was saying, from history, we know that rotation curves were observed, and they were actually theorized to follow a Keplerian law, but they were observed to found that they flatten out at higher radii. So if you can see on the plots on the right hand side, you can see the actual data points actually flatten out, or in fact increase in some cases. So this deviation led to formation of the dark matter theory, and since then there have been ton of research going on. There have been theories proposed of what the dark matter is actually, and there have been theories for how the density profiles might vary. So here what we do is the decomposition of this rotation curve, which we break down into their own components, that is disk, bulge, and the dark matter halo. So for doing this, what we did is we followed the generic methodology that is followed. We went ahead and if you could scroll down, please. So yes, so we went ahead and we saw the disk velocity profile, the bulge velocity profile, and the halo profile. So for disk, we use the exponential spheroidal model, which basically takes exponential surface brightness increase along the radius and surface density increase along the axis of the rotation. And for bulge, we use the de Vanquist profile, which is a special case of Sersic with index as 4. If you could please scroll down. Right. So for the halo, that is the dark matter halo, there have been numerous density profiles that have been proposed, and they are being tested right now since it's a very young subject. We chose a Navarro-Frank White, that is the NFW profile, because it holds very well with the cold dark matter universe. And since we are dealing with spiral galaxies, that is a widely accepted choice. Now, using all these separate components of velocity curves, we made a combined equation of velocity. And we tried to fit this using, if you could scroll down, please. Yes, perfect. We used least square fitting from MATLAB, and we tried to fit this data. So we altered the initial conditions so that we get the chi-square value nearest to 1, so that the free parameters can be recorded, and after which we performed certain calculations to find the mass of each component, that is the disk, bulge, and the halo. Now, so for performing the after performing the chi-square, if you could scroll up to the right-hand side. Thank you. So in SOFU 2015, this is a very significant paper which works on decomposing of rotation curves of over 100 galaxies. So in this, they have mentioned this criteria which describes a good fit for any kind of rotation curve decomposition. And we found that our fitting algorithm was upholding this criteria. And the plots that you can see are basically the plots that are decomposed. So the red plot is the data plot, and the pink is our fit. And the dotted lines that you can see are basically for bulge, halo, and disk, respectively. So if you could scroll down. Thank you. So the table that you see on the right-hand side, that describes the chi-square values and the mass ratios. So what we did is, after recording the free parameter values, we calculated the mass of disk, bulge, and halo separately. We added them together and we found the ratios of each segment. And so going to the conclusions and future scope, as you can see, this is a very small sample of 5 galaxies, and our main motive was to check whether the fitting algorithm is working well. So you can see that chi-square is almost near to 1, and it's also upholding the scale radius criteria which was mentioned. So the fitting algorithm works very well. And here we showed the ranges of the ratios that we have found. But again, 5 galaxies is quite a small sample in order to get a statistical dominance. So what we plan to do is increase this sample size even more and test it out for larger number of galaxies, perhaps even with different morphologies, in order to see how morphological changes will affect the fitting. So of course, I'd like to acknowledge this research. Initial part of this research was done with Todd Ayres Research Institute and our mentor Sundar MN for helpful discussions. And that will be all from our side. Thank you.
Thank you, Prateek, for being on time. We have questions from the judges. Please go ahead.
Hello. Prateek,
yes, sir.
This particular work completely done by you or your team?
Yes, sir. Yeah.
Okay. First thing you were telling regarding the spiral galaxies you were looking for this dark matter probe, right?
That's right, sir.
So, which type of spirals and all these things in a very short while, can you tell me?
Of course. So we are currently the presented study focuses on SB category only. But as I mentioned in future scope, we will try to see different morphologies within SB, that is SA, SB, SC, and we'll see how the spiral arms will affect the rotation curves and further the fitting.
And how you are getting assured that you are going to get the dark matter exactly from there?
I didn't get you, sir.
Means, of course, for the dark matter probe, you are presenting this particular paper.
Right, sir.
So, how you can get yourself assured that yes, means which particular thing can tell you that yes, you are going to get some dark matter there?
Right. So that basically comes down to how the profile is actually. So if you could zoom into the fifth plot, if that can be done. Yes. Perfect. Thank you. So, so if you can see in this plot, you can see that it is almost adhering to what Kepler had predicted or how it should follow the Kepler's law. So the green line depicts the disk profile and the the green line depicts the halo profile. So this basically tells that I mean, based on the overall way the rotation curve is seen, we can say that the dark matter is present or not. And from the fitting parameters, once we have calculated the mass of halo and disk and bulge, we can see the ratios as to how much of the dark matter is present and how much it is not. And just like you said, it is very much possible that the dark matter is not present at all, but we should be able to see in the masses of those fittings.
Fine, thank you. I think Dr. Chaudhary having some question.
I have a question. Sorry, I think I had kept my microphone off. Sorry. Yeah, Pratik, in the fitting of the velocities. Hello.
Yes, sir. Yeah.
Yeah. How are you? I mean, you're just plain adding them up. I mean, is that the way to go about it, or for the three contributions?
Right. So that's actually a very good question. So we basically take the total velocity square is equals to the square of each component. So that's how it's supposed to go.
Mm-hmm. And how do you know that this is correct?
It's based on literature survey. That is one way. I mean, that's a very weird way to answer. But technically speaking, if we go direct summation of the velocities, it would result in root as the first component for everything. And that would basically minimize the error and it would affect in the fitting. So that's why it's generally preferred of squaring and adding the components so that the errors are not altered much.
I see. Okay. Thank you.
Thank you, sir.
I just wanted to know, are you a PhD student?
No, sir, I'm a bachelor's student.
Okay. So that means this is a part of your BTech project.
Not really, sir. This is like a separate thing entirely.
Okay. Sure. Thank you.
Thank you, sir.
Okay, so if we are done with the questions, we will go ahead with the next presenter, Shazuddin Ahmed. Do we have him with us?
I am audible, ma'am.
Yes, you are.
Okay. A very good afternoon to everyone. Myself, Shazuddin Ahmed. I am a student of MSc 4th semester, Department of Physics, Rajiv Gandhi University. And this poster is made on the basis of my third semester project. And my work was proceeding with theoretical modeling, where I use Young Laplace equation, and in experimental approach, I growth the zinc oxide nanoparticles in PVA matrix, and then I take absorption spectra, and then I um, determine the structure size of the nanostructure. Then at first I briefly tell about the theoretical approach. Can you please scroll down this to result? Okay, here I consider two nanoparticles of different size, and Young Laplace equation gives their potential, the chemical potential. Due to their different size, their chemical potential will be different, and the difference of the chemical potential which depend on the temperature and vapor pressure of both the nanoparticles. And when we increase the temperature, there the portion del D divided by D2 D1 will be increased. Can you scroll more, please? Here it is observed that when temperature will be increased, the particle size difference will be increased. That is, if we consider T3 is greater than T2, then T1 and T, then at higher temperature, the particle size difference will be maximum. Can you, ma'am, please scroll up to the right side? Okay. This is my experimental approach where I grown the zinc oxide sample in PVA matrix at different temperature, 30 to 55, 75 and 90 degree centigrade. And here it was clear that their apparent density was increased with increasing temperature. After this, I take the absorption spectra, and all the peak was absorbed at the bandage absorption. And from this peak, I have calculated the energy band gap. And after this, I have calculated the nanoparticle size using the equation, effective mass approximation equation, and then I get that at higher temperature the particle growth was more. Can you down them? So in conclusion, I can say that in both theoretical and experimental works coincide with the same result, as when increase the temperature, the growth of nanoparticle will be more. That is my words. Thank you for listening.
Chais, why should the chemical potential go inversely with the diameter?
Yes, sir.
I'm asking, why should the chemical potential go inversely with the diameter of the nanoparticle?
Because, sir, when particle size will be increased, then their chemical potential will be decreased due to surface energy.
What is chemical potential?
The chemical, sir, chemical potential actually is sir, sir, it's like potential energy, sir.
Can you please explain a little bit about that particular calculation of size of NPS from band gap?
Sir, particle size, sir. Sir, I have used this formula, sir. Effective mass approximation, this formula, and I have calculated band gap from the absorption peak, where I get absorption peak, and from this I have calculated band gap, and using this effective mass approximation formula, I calculated the size of nanostructure.
Okay, and two more things I will ask you. That particular graph, I can't see that graph clearly. Yeah, here, this bar
Yes, sir.
actually. Uh, can you explain this little bit? The last one, with this calculation of size of MPs.
At 90 degree, this one, sir.
Last
Someone
one.
mentioned the temperature, maybe.
Yeah?
Are you asking that absorption spectra
No.
or growth temperature versus particle size?
Growth temperature, right? Growth temperature. I couldn't read that. Growth temperature versus.
Can you, sir, repeat your question, sir, please?
No. Can you just little explain that one? That growth temperatures, that particular plot. I can't hear clearly. Sorry, read clearly. That's why I'm asking.
You have to explain.
Here, sir.
Yes, Coulomb plot. Growth temperature versus particle size. That plot you have to explain.
Yes, sir. Here, sir, I have calculated nanostructure size with corresponding the temperature. Then I plotted this, and at 32 degree, the growth was minimum as compared to 90 degree, and when increasing the temperature, the growth was more, and I use this as SART graph.
Why you think this is changing?
Because when the temperature, they were prolonged growth there, as when their size is small, they're thermodynamically unstable.
Okay, fine. Thank you. Any other question?
If there are no more questions, then thank you, Shais. We will move to our next presenter, Harish Reddy Inta. Do we have Harish with us? Okay. Before that, can I ask Junik Sengupta to kindly switch off your video? That helps us to have a good network.
Yeah, go ahead.
Okay. Good afternoon to all. Sarala, can you move the slide up?
Harish,
Yeah.
at first you please introduce yourself.
Yeah.
You are MSc, PhD, or what student like that?
Good afternoon to all. Myself, Harish Reddy Inter. Currently, I'm working as a research scholar under the supervision of Professor Venkataraman Mahalingam at IISER, Kolkata. In this poster, I am presenting about the fabrication of the nickel selenide MOS to interfacial structure, and this material was utilized for catalyzing hydrogen evolution reaction in alkaline medium. So, as you all know that currently hydrogen fuel is getting more attention since it is having a higher energy density as compared to the conventional fuels. On the other hand, the fuel is associated with zero carbon emission, which could be beneficial for from the sustainable point of view. In this regard, electrocatalytic water splitting reaction is one of the efficient ways to produce the hydrogen gas in a clean and efficient manner. As you all know, that electrocatalytic water splitting reaction is associated with two half cell reactions called as hydrogen evolution reaction and oxygen evolution reaction, where the hydrogen gas and oxygen gas will be produced from the cathode and anode respectively. The current, however, the thermodynamic potential for catalyzing water splitting reaction is about 1.23 volt, In addition, the kinetics associated with this reaction is pushing the thermodynamic barrier to further high. So it demands the development of efficient electrocatalyst to facilitate the facilitate the water splitting reaction at a relatively lower potentials as close as to the thermodynamically equilibrium potential. The current state of art electrocatalyst for catalyzing hydrogen evolution reaction and oxygen evolution reactions are platinum and ruthenium oxide respectively. However, since they are scarce in nature, there is a huge demand for the development of electrocatalysts from the earth-abundant materials. So in this poster, I will be talking about hydrogen evolution reaction in alkaline medium. Since it is challenging as compared to the hydrogen evolution reaction in acidic medium because of the sluggish kinetics originated from the water dissociation process, where the water molecule needs to dissociate first to produce the hydrogen atom onto the catalytic surface. From there on, the hydrogen molecule formation takes place. This is challenging in alkaline medium as compared to the acidic medium, since the proton is readily available in the acidic medium. So the catalysts which work efficiently in the acidic medium, they tend to lose their activity by several orders in alkaline medium because of the additional step that I have mentioned previously. Yes, and in this regard, transition metal dichalcogenides like MOS2, MOSE2 are known to be a good electrocatalyst for hydrogen evolution reaction in acidic medium. However, they are also lose their activity in the alkaline medium. So people came up with an heterostructures where they combine some water dissociation promoters with these transition metal chalcogenides to accelerate the HER kinetics. So the efficiency of the catalysis is usually depend on the significant interaction between the water dissociation promoter and the MOS2 surface. So by keeping in this mind, we wanted to prepare a heterostructure of making heterostructure of nickel selenide MOSE2. For this, we have chosen two-step solvothermal synthetic route, where initially we have prepared Ni 0.75 Se nanoparticles by reacting nickel salt and selenium salt at solvothermal conditions around 180 degrees for 24 hours. Subsequently, the produced material was injected into the precursor solution of sodium molybdate and selenium. After the hydrothermal reaction, we obtained nickel selenide MOSE2 heterostructure. So after that, the prepared materials were characterized by using XRD and XPS analysis. Sarada, can you go to the left bottom? Yeah, the figure 1 here is showing the XRD pattern of the materials synthesized from the autoclave hydrothermal reactions. In the case of as prepared Ni 0.7 SC, the XRD pattern display a sharp diffraction pattern indicating the monocrystalline nature of the material. In contrast, the pure MOSE2 displayed amorphous peak, suggesting the broad peaks in the XRD pattern, suggesting the amorphous nature of the material. In the case of composite, we can see the peaks from both of the components, indicating the formation of heterostructure. In addition, the peaks that are present at the lower angles has been disappeared of the composite formation, indicating that Ni 0.75 SE has been transformed into Ni 0.85 SE during the composite formation. In the case of XPS, in the composite display the peaks from both Ni2 plus and Ni3 plus ions, indicating the presence of different kind of nickel ions in the system, and the pattern is closely matches with the previously reported Ni 0.85 SE system. And this is in again a good agreement with the XRD analysis that I mentioned before. In the case of molybdenum, we have seen a peaks from 3D 5x2 and 3D 3x2 at the corresponding binding energies of MOS Se2, which is in 2H phase. And we found that the material surface got oxidized, and it is evident from the XPS pattern of selenium, as we can see from the figure 1D. After that, we have recorded the image SEM and TM analysis of the materials. Saurabh, can you go to the top right? The as prepared NI 0.85 SE displayed a three-dimensional net-like structure where the nanoparticles were interconnected together to form chain-like chain-like structure. In the case of MOSC2, a three-dimensional flower-like morphology was observed, where it is composed of two-dimensional flakes. In the composite, we can see the presence of nickel selenide and MOSC2 components, and the figure 2F is displaying the boundary between the MOSC2 and Na 0.85 SE system. So this heterostructure, the interfacial structure could be beneficial for the polarizing water molecule, as it has a distinct electronic distribution at the interface. Coming to the electrochemical studies, for the measuring hydrogen evaluation reaction efficiency of these materials, we have drop casted these materials onto the carbon paper. Subsequently, we have recorded the polarization curves in the potential range of 0 to minus 0.4 volt with respect to NHE. And while increasing the potentials from thermodynamic potentials, there is an increment in the current densities observed from the materials. However, among all the materials, the interfacial structure could able to deliver high current densities at relatively lower potentials as compared to its individual components. And after the composite formation, the MOSC2 catalytic efficiency has been significantly improved. As you can see from the bar diagram, is displaying the current density that displaying the war potentials that are required to deliver a benchmark current density of 10 milliampere per centimeter square. The MOSC2 required around 160 millivolt to deliver this 10 milliampere per centimeter square current density. After the composite formation, it got reduced to 108 millivolts, suggesting the improvement in the catalytic efficiency of the material. After that, we have performed Tafel slope analysis to understand the reaction kinetics of the materials. Here, I want to specify that the Tafel slope of MOSC2 is reduced from 80 to 70 millivolt per decade, which is indicating that there is a slight improvement in the reaction kinetics, which could be occurred due to the heterostructure formation. Interestingly, we also found that the electrochemical active surface area of MOSC2 has been doubled after the composite formation, which is reflecting from the increased double layer capacitance values of the material. Again, the next plot is indicating the better charge transfer kinetics of the heterostructure as compared to MOSC2. And then the cyclic stability experiment is one of the important technique to figure out the efficiency of the material for the long-term application. And for that, we have performed cyclic stability experiment up to 2000 cycles. And even after 2000 cycles, the material could maintain its catalytic efficiency, but then we found that very slight improvement in the war potential was noted even after 2000 cycles, indicating that its robustness of the material for long-term application. Coming to the conclusion, we could prepare NI 0.85 CMOS interfacial structure by using two-step solver thermal method, and the composite formation lead to the enhancement in the alkaline HR kinetics by facilitating water dissociation process, as well as the heterostructure improved the number of active centers available for the catalytic process to occur. So by using this material, we have also demonstrated overall auto splitting reaction, and for those details, you can visit this reference as I have shown here, and that's all.
Thank you, Harish. Do we have any questions from the judges? Okay, so if we don't have any questions, then thanks to Harish again for presenting a good work. I would like to check whether Manjit is still here with us or Manjit Bora.
Let's continue.
Okay, so if we don't have Manjit with us, then I would like to conclude the poster session by saying that it was indeed interesting and exciting to see how people working so hard in different stream of science have come together to put their posters. And it was a truly interdisciplinary session that we had. Thank you to all the speakers. And now we will move on to our next and the last session of this conference, which will have a series of talks by the eminent speakers. And and the first speaker of today's session of important talks, we have Professor Arup Kumar Das.
Yeah, I'm here.
Okay. So to introduce Professor Arup Kumar Das, he is Associate Professor in the Department of Mechanical and Industrial Engineering, IIT Roorkee. He received his MS and PhD from IIT Kharagpur and then did his postdoctoral research from UPMC, France. His current research area is focused on two-phase flow, microfluidics, boiling heat transfer, and numerical methods. So without further ado, I shall invite Professor Arup for his talk.
Thank you, Dr. Mukherjee. So I think that, if I switch off the video, then the bandwidth will be better. So
yes, of course.
Let me switch off the video and try sharing my slides. So please let me know whenever it is visible at your end.
Yeah, sure. Yes, your slides are visible.
Fine.
Yeah.
Thank you. So thank you once again, Dr. Mukherjee, for this nice introduction. So I am actually working as Associate Professor in the Department of Mechanical and Industrial Engineering, IIT Roorkee at present. And as it has been introduced that I am actually working in the area of two-phase flow. So today I'll be giving you a little bit idea that in our lab at IIT Roorkee, how we are developing some sensors to detect the phases. Okay, so what are the developments are going on, and what is the range of operation, that also I'll be telling you. So my title of the talk is like this: detection of phases with indigenous sensors, and I'll be talking about developments and range of operations. But before going into detail, let me once again congratulate to the organizers for this first international conference on convergence of Interdisciplinary Science 2022. If I try to give a little bit idea about what is two-phase flow, so here I try to give some idea. Mainly there are different types of phases like solid, liquid, and gas. We are well aware about, and my work is where two or more phases are actually coming to, in contact with each other. Okay, so for example, if you see this Venn diagram, so you can see that single phases are associated over here as gas, liquid, and solid, but we may also have gas-solid interaction like this, which is a powder flow kind of interaction. We may also have gas-liquid interaction. Okay, so in this snap, you can see in a pipeline, air bubble actually is moving up due to buoyancy. Okay, inside some liquid medium, and side by side we may also have solid liquid interaction. Okay, perfect example of solid liquid interaction is droplet resting on a solid surface. And side by side, we may also see that there are presence where three different phases are together. So perfect example is, whenever iceberg is melting, there are various other examples. Quickly, I'll go through some of the examples to make you familiarized with the topic, whatever we are going to discuss. So for example, where we see the two-phase flow in nature, okay, starting from water waves. Okay, we can see the devon leaves, we can see the geysers. Okay, obviously we can see in the waterfalls. Okay, and rain, that is also a critical example of two-phase flow. Okay, and if we go further in our daily life, whenever you sweat, we do some work in kitchen sink. Okay, emptying a bottle, you can see presence of two phases, gas and liquid. Sprinkler, obviously droplets can be seen in the atmosphere of air. Whenever you are trying to mix coffee in your cup, so you can see the presence of bubbles. Pouring the glass, so everywhere you can see around us we are having presence of two-phase flow. Okay, so this is actually shower and your toilet basin, soap foam, that is actually peculiar example of two-phase flow. In our lab, we are actually doing some studies on the carbohydrate drinks. So there also you can see foams are there, shaving foams, buttermilk. So there are various examples. I'm showing you some of the pictorial views over here. In sports, we may have different directions where we will be having two-phase flow, and knowledge of two-phase flow helps. For example, swimming to ice skating. Okay, Summer Olympics to Winter Olympics. Okay, everywhere you can find out presence of two-phase flow. Some more examples I have shown you over here. Okay, spider waves, sandstorm. Okay, this is Geneva fountain basically. Okay, so there are several other daily life occurrences for two-phase flow. If I come to the industrial occurrences or industrial presence of two-phase flow, pneumatic conveying, cyclone separator. In machining, we use water jet machining for cutting metal. Okay, so there also a two-phase liquid jet you can see over here. Okay, so that cuts the metal. Using liquid, you can cut a metal, solid metal plate. Fuel injector, this is for our cars and IC engines. Okay, so you'll be having slurry transport pipelines also many places. So they are also solid liquid two-phase flow we can see. Okay, so apart from that, it is very useful in case of nuclear reactor, oil exploration leak. Okay, and cooling towers. Okay, different condensers in air conditioning and refrigeration plants will be seeing two-phase flow. Let me not go into further detail of industrial application, but straight away let me first introduce few nomenclature. As we have mentioned that I'll be giving you some idea of measurement techniques in two-phase flow. So what are the measurement quantities we are having? So first of all, we are very much interested to know what is the void fraction. Why void fraction is necessary? I'll try to give you the idea of what is void fraction. So this is just nothing but a cross section of a pipeline where two phases are occurring, you can see. So consider the blue colored part is actually liquid and the white colored part is gas. So they are in close association with each other inside a pipeline. So you may find out that they are not, in a stratified manner they are staying, or in a concentric manner they are staying. So there is some sort of boundary between the liquid and the gas phase you can see over there. Usually we call that one as interface. Okay, so now what is the interfacial shape and size? Depending on that, the property transfer happens. Now, what is property transfer? There are different types of properties. For example, if there is chemical reaction, so obviously there will be some sort of species transport, transformation from one side to another side. If that is related to heat transfer, so we can see thermal energy actually transfers from one phase to another phase. So like that, transfer of properties actually causes different processes to happen. So it is very important to know that what is the interfacial shape and size. So to know the interfacial shape and size, we are very much dependent on the quantity like void fraction alpha. So what is alpha? Alpha basically we say as the area occupied by the gas, which is Ag, you can see the shaded portion of, in white, divided by the total area where the two-phase flow is occurring. In this case, it is actually a circle, okay, a pipe, that's why it is a circle. So that is called alpha. So, apart from this void fraction, we are also interested to know what is the mass flow rate. So mass flow rate, obviously the corresponding densities will be coming into picture. So you can see that along with the velocity, by the way, velocity is represented as U over here, along with velocity and area, the density, okay, of the respective phases will be also coming into picture. So these are individual mass flow rates of the gas. G symbolizes gas and F symbolizes liquid over here in a gas liquid mixture. And the ratio between these two we call as quality. Okay, so usually quality is defined X, which is very important parameter over here. As many industrial processes we actually discuss about the quality. So that is nothing but actually Wg by W. That means the overall mass flow rate when we add both the liquid mass and the gaseous mass. So overall mass flow rate, how much percentage of overall mass flow rate is the gaseous mass flow rate, that is called quality. So these are the two important parameters, void fraction and quality, which we deal with in all our two-phase flow examples. So with this idea of occurrences, daily occurrences of two-phase flow and little bit notation idea, let me go ahead how we actually measure it. Okay, so if I now show you that how we measure it. So for measurement of two-phase flow, there are different types of principle of sensing. Okay, so we can measure two-phase flow based on the different techniques like conductivity, capacitance. Okay, by the way, what are these techniques? These techniques are nothing but differences of conductivities, okay, between the phases. Okay, difference of capacitance between the phases, optical properties like photography we use sometimes. We use light attenuation properties. Okay, so those are called optical probe, capacitance probe, conductivity probe for two-phase flow detection. Not only these easily available methodologies, there are some high-end available methodologies also, like X-ray we also use, gamma ray, neutron ray, radio frequency waves, okay, and different other like magnetic field also sometimes we use, ultrasonic. So all these probes we have to develop in-house for understanding the interaction between the phases. Okay, so these are the techniques we use. I'll be showing you today one or two of these because all these methodologies are time-taking to describe. So let me quickly go ahead that how we measure the void fraction alpha. Just now I have shown you. So the mundane method for measuring the void fraction is that you have to have two quick closing valves. Okay, what is quick closing valve? Maybe we have seen in our kitchen sink or in our washroom, we can see there are valves. Those are actually called quick closing valve. But only thing is that these valves are actually having some turns which you need to rotate to completely close the flow. Quick closing valve can, within a fraction of a second, it can completely close. So what we do over here, let's say this is a pipeline, okay, and in this pipeline, this is a vertical pipeline. Let's say, consider the black color is actually phase 1, and let's say the white colored things are actually phase 2. So what we do, we allow the flow to pass through a vertical tube or channel, and then there are two quick closing valves, one at the bottom, one at the top. So first we close this bottom quick closing valve, and then after some time we close the top quick closing valve also. Okay, so once we do that, we can trap some amount of two-phase flow, okay, inside this small pipeline. And as the phases are having their different properties, mainly density over here, as we are having different densities, so you can find out due to buoyancy, the lighter phase will be actually separated over here. Okay, as you can see that all those white colored spherical or circular phase 1 presence is actually converting into a stratified one due to buoyancy. It will take time, and at the bottom you can see the heavier fluid will be actually coming down. So if it is gas liquid, you can find out this is the gas and this is the liquid. So from here we can actually identify that how much is the presence of gas and how much is the presence of liquid. As I have told you, this is actually mundane methodology. Always it will not be possible to stop our flow like this using quick closing valve and then measure the phase fractions, okay, void fractions basically. So these methodologies are no longer popular nowadays, and it is associated with error also, because it depends that how the operator is closing quickly these two valves. Okay, so that's why we need to go to this kind of techniques, whatever just now I have told you. So earlier days, what we used to do, we used to actually take the help of the analog circuits and signal processing units. Okay, so analog circuits are mainly based on some mechanical arrangement. So here you can see a mechanical bio is there, and this is actually floating on top of some some piston cylinder mechanism over here. And if the two-phase flow is occurring inside a pipeline, the pressure is being sensed in both sides of the piston. Depending on the pressure, you can find out the piston will move up and down, and the bio, as it is connected with the piston, the bio will move, and the bio is connected with the stylus over here. On a graph paper, it will be drawing the the lines over here, and depending on the pressure difference inside this, the line will be actually drawn over the graph paper. So this was the primitive methodology for measurement of two-phase flow. So the recent version is that we actually came to this analog system, and finally using devices like polar planimeter and ink brush, magnetic oscilloscope, we can actually convert this kind of signals into a readable signal, so that we can understand that what is happening inside the pipeline where two phases are present. So you can see over here, phase 1 is the continuous phase, which is filled up inside the pipeline, and phase 2 are actually the discrete presence of the gaseous bubbles. Okay. So now I was telling you the graph paper, so on which the stylus will be drawing. So this you can see, this is the draw of the stylus for one particular case. So this is the situation where reweighting front of one gas liquid phase we are actually tracking to see. By the way, what is reweighting? Sometime we'll be finding out that whenever two-phase flow is occurring, so there will be one weighting front, which is actually, weighting front is nothing but liquid and gas junction, which is actually moving up inside the pipeline. So sometime we'll be finding out that not only weighting, there is another front which will be following the weighting front. We call that one as reweighting front. So the reweighting front velocity we try to predict over here. You can see the temperature versus time we have plotted over here. So the difference between two peaks, we can find out how much time, and then from there the velocity can be estimated. So this kind of measurements were there earlier. Nowadays, we have moved to some digital-based systems, and you can see that in place of polar planimeter and then stylus and recorder, we are moving to data acquisition system, which is completely electronic system. And in a computer, we can actually find out the graphs. But the sensing techniques are remaining same. Sensing techniques means what I have told you, that using the basic property of the phases, we try to understand that how much is the interfacial interaction. Okay, so as I have told you, that not only the sensing technique, some sort of processing of signal is also important. Whatever signal we receive, processing of signals are also important. So in our lab, we do different types of signal processing, what we obtain from the probes, okay, based on different techniques which I have mentioned. Some of the methods are like this. We go for edge detection, pattern recognition, cross correlation, okay, and different types of AI-based techniques also we develop. Side by side, some signal processing methodologies also we follow, which are statistical in nature, like evaluating the PDF, probability density function, power spectrum density function, Fourier transforms, and wavelet analysis. Quickly, I'll be trying to show you some. Here also we do some sort of AI-based algorithm or neural network-based algorithm. So I'll take one or two examples. First of all, let me show you this example. So this is gas liquid upflow through concentric annulus. So pipeline, all of us have seen. Okay, now if there is some obstruction in the pipeline concentrically, so then it will be creating one concentric annulus passage for the flow to happen. Okay, so consider in that concentric annulus, we are having gas liquid flow, which is moving in the upward direction against the gravity. So in that case, how to measure the void fraction? So here we have actually used our indigenously developed sensor-based conductivity plate, sensor and parallel plate-based conductivity probe, and the signal has been analyzed using probability density function. So it is, you can call this is a single sensor, single feature estimation kind of analysis. So I'll give you quickly some idea about how the conductivity probes are constructed. So these are the conductivity probes, very simple. Two wires we allow to pass through the pipeline. Okay, this is the cross section of the pipeline, very thin wires you can see. Now what happens whenever two phases are actually running inside this pipeline, you'll be finding out sometime the gas is touching this, this one of the wire. Okay, and as a result, you'll be finding out that if I allow electrical signal to pass through it in presence of gas, the density or the resistance of the wire will be very high, and in that case there will be a sharp fall in the voltage measured. Okay. On the other hand, if there is actually liquid medium around these wires, so you'll be finding out that resistance is lesser, and you will be finding out that there will be actually a very high voltage. So seeing the voltage, we figure out that what is there in between these two wires. And as a result, we figure out that what is the medium going through inside the pipeline. So there are different versions. This is parallel wire version. In here you can see that ring type of conductivity also we give along the concentric annulus. Here you can see this is the concentric annulus. In the inner side of the concentric annulus, we give this kind of conductivity probes. So quickly I'll be showing you that what are the processing circuitries. So these electrodes we use in the Wheatstone bridge. Okay, so this is Wheatstone bridge, and then we use our wind bridge oscillator to give the charge to this Wheatstone bridge, and to rectify the signal whatever we are getting from the unbalanced arm of the Wheatstone bridge, we actually go through some amplifier and precision rectifier and some filters before taking the signal for our study. Now, quickly, I'll be showing you some of the situations. Let's say you consider these two figures. So here you can see very tiny bubbles are present. That means the secondary phase, which is gaseous phase, is well dispersed in the annulus regime. Okay, but whereas here, if you see the figure, you can see some larger sized bubbles are also there. Okay, bigger sized bubbles. These are actually bullet-shaped bubbles. We call this one as slug bubble kind of scenario. Okay, so you can find out now whenever we have taken the signal, you can see this is the signal, raw signal. Okay, here this is the raw signal. Now, if we do the PDF or probability distribution function of this signal, you can find out a peak like this. Okay, a peak like this you can find out. So these two cases are more or less similar. We cannot identify difference between these two as we are using single probe and single technique for signal analysis. But you can see some flow regimes can be understood. For example, here, this one you can see, this is a very big bubble presence over here. We call this one as the Taylor bubble. Whenever all those smaller bubbles shown in the previous slide merge together, and then they form a bigger bubble like this. We call this one as the Taylor bubble. So in this case, if you see the signal, this is completely different compared to the previous one. Okay, previous one you can see that the signal was very much random like this. So if we do the probability density function, then you'll be finding out that we are having two different peaks, one at higher voltage side, one at lower voltage side. So now, if we are knowing that signal, what is the probability density function, you can always predict back that what kind of flow regime is actually occurring or what is the interfacial configuration. So here, using one single probe, I have shown you that how interfacial interaction or void fraction can be tracked without knowing about the flow configuration. Many times the pipelines will not be actually visible from outside because those are metallic pipelines. So how, using this kind of conductivity probe and the signal analysis, we can actually understand the regime behind. Now, I will not take much time as we are running behind the schedule, I understand. So I'll be showing you one more analysis where we are actually using multiple probes and multiple signal analysis. Sorry. Yeah. So this is the situation I will show you where we are actually using one optical probe. Okay. So you can see over here. Here I tried to show you same thing, but now I am going for liquid-liquid mixture in place of gas-liquid mixture. Okay. So here what we are doing, not only a single probe like electrical conductivity probe, I am using electrical conductivity probe along with some optical method also. So two different probes or sensors we are using. Okay. And for the analysis of signal, we are using PDF, which I have shown you in the previous one. Along with that, we are also using wavelet. Okay, so wavelet is nothing but it tracks the frequencies, okay, and the standard deviation, and it gives us the decomposition of the frequencies. Okay. So previous one, if you have seen, we have not understood properly the difference between, the bubbly flow situation where lots of bubbles are there of dissimilar size, and dispersed bubbly flow situations where bubbles are more or less of similar size. But we can easily understand the difference between bubbly flow and slug flow situation, okay, using single probe and single PDF mechanism for the signal analysis. But if we do multiple probe and multiple feature analysis, then how it works. So this is some pictorial view of the industrial setup where this kind of studies we are doing. Okay, so this is actually for oil and water. Mainly we are using kerosene oil and water mixture. Okay, these are very popular for oil exploration leaks. Okay, and you can see what we are doing. Conductivity probe I have shown you earlier. I am not showing you once more. Here we use optical probe. This is one optical laser you can see. And on the other hand side, we are having one receiver. Now, whenever laser will be passing through this, depending on the medium present in between, it will be actually attenuating the power over here. So if it is completely filled up with kerosene, whatever power will be getting. On the other hand, if it is completely filled up with water, different power will be actually attenuated over there. So as a result, whenever these detectors will be connecting with the processing circuit and subsequently data acquisition, we can measure different voltage signals. So here we are having one optical probe signal as well as one conductivity probe signal. Both the things we are having together. Two sensors we are using over here. Two different types of sensing methodologies or techniques we are using over here. Now, along with that, I'll quickly show you that what we are doing. So we are having the data of PDF, which we get from the conductivity probe analysis. And from optical, we are trying to do the wavelet analysis. So quickly, if I tell you what is the wavelet analysis, this is actually acting as a bandpass filter. It gives a good time resolution, okay, at high frequency, and good frequency resolution at low frequency. Okay, so mainly we can say that wavelet is actually multi-resolution feature. So little bit idea about wavelet I have given over here. You can see basically a signal is actually decomposed into its different dominant frequencies D1 to D5. Here it is fifth order wavelet frequency I have used. It can be done for many more layers, and this is the residual obviously. So you can see what we do. This signal first, this is the average. Okay, we can take the window of averaging also. So it is the average, and then this minus this is this D5. So once again from D5, if we do once again averaging and the differentiation as I have done for A5 and D5, we get D4. Then subsequently it is D3. Like that we can go for different layerings. So here I have done for 5 layerings. Now you can see with this PDF and this wavelet analysis, I can clearly understand the difference between the bubbly flow. Here this is the bubbly flow signal. You can see D1, A5 I have shown side by side, and PDF is like this. This is bubbly flow scenario, and you can see this is the other flow signal which I have shown you previously, dispersed bubbly flow. You can see the values of A5 and D5, these are different. So please concentrate on this one. Here we can see the D1 to A5 and then S, okay, complete signal standard deviation, and then D1 to D5 and A5. So the pattern is completely different in case of dispersed bubbly flow as compared to bubbly flow. You can see this is now a completely falling trend for D1 to D5. Okay, so now you can see that whenever we are using multiple sensor and multiple feature analysis, then we can actually figure out the finer details, like how the two phases are actually associated with each other. Okay, so these are some demonstration of the indigenous probes which we are actually using in lab scale for evaluating the phase interactions, which are very important for issues like mass transfer and phase transfer in industrial applications. Okay, so with this small one, let me stop. So what I have done over here, if I can give some sort of summary for as a take-home message. So we have actually listed all possible techniques for measurement of two-phase void fraction. I have shown you some constructions and working principle of conductivity probe and optical probe. Okay, and fundamental of probability density function, and using optical probe, how wavelet analysis can be actually we can do for analysis of finer details of the signals, and using that how we can track the interfaces that we have discussed over here. Okay, with this I would like to thank you, and organizers also I'd like to thank you for calling me over here. Thank you.
Thank you very much, Professor Arup, for this nice and very clear presentation. And I would like to ask if anybody has any questions. Okay, so if there are no questions, then after this very interesting talk on sensors, we will proceed to our next talk, which is, the speaker is Dr. Amit Pathak. Dr. Amit.
Yes, I'm here.
Okay. Dr. Amit is professor in Department of Physics, Banaras Hindu University, and he completed his PhD from DDU Gorakhpur University in 2006. And he is actively involved in research related to detection of PAH in the interstellar medium. And his current research interest includes astrochemistry and astrobiology. So I welcome Dr. Amit for his talk.
Yeah, thank you very much, Shritama. And I'm delighted to be presenting my work here. And I also thank the organizers for giving this opportunity, actually. So I'm going to share my slides now. Okay, so I hope it is visible.
Yes, you can put the slideshow.
Yeah, I think I have started the slideshow.
Yeah, for some reason the slides are not coming in full screen. Can you just stop sharing and share it again, maybe?
Yeah, sure, maybe. Now, is it okay?
We can see the slide, but yeah, not in the full screen.
Not in the full screen?
No.
I don't know why this is happening. Because I can see it, I mean, here on my laptop, it is full screen.
Maybe you can do that full screen. You share the full screen.
Oh, share the full screen.
That will be.
Okay. No, but how do I share the full screen? If I make it full screen, then I cannot go back to the. Does it work now? Is it okay?
No.
Not. Oh, I don't know. I mean. Now, does it work?
No.
No. I don't know what is going on. Not yet?
No.
Okay, so what I'm going to do, just give me a minute. I'll just try to. Maybe. One last thing which I want to do is. Now? Does
yes,
it work?
this works. Yeah.
Okay, I don't know. I mean, why is it not working? Because I wanted to use the PPT, but I'll use the PDF now.
Yeah. Okay.
Yeah, I had some GIFs which might not work here, but that's all right. Okay.
Okay.
So what I do is I work on molecules which might be present in space. Some of them are already detected. Some of them are yet to be detected. So here I'll be presenting about the largest one, the biggest one, which I mean, one of which is already detected in space, and the other family is yet to be detected. So we do mostly spectroscopy and some reaction-based, but all of the work is actually theoretical. So I mean, this slide shows large number of molecules. I don't want you to read all of it, but the highlight of this slide is that the most of the molecules, I mean, this slide shows that which molecules have already been detected. Okay, so you can see that small molecules like hydrogen, for example, and coming to the bigger ones, like for example, fullerene has been detected. But the highlight is that most of the molecules that have been detected are organic in nature. They have carbon, they have, I mean, some of them also have nitrogen, some of them have oxygen. And you can see here most of the molecules, except for a few, have dipole. Okay, so they are polar molecules, so they have rotational spectra. So most of these have been detected using rotational spectroscopy. Okay, not the UV visible, not the IR, but rotational spectroscopy, because rotational spectroscopy gives you the unique identification characteristics which the infrared and UV or visible do not actually. So coming to this slide actually tells us where these molecules are and how these maybe, I mean, what kind of signature is expected. So here I have I mean, see, suppose we have a star here, and the molecules are in these big chunk of clouds. So these are known as molecular clouds. So most of the star formation activity takes place in these clouds. If we have a star and we try to record the spectrum of the star, what we see is a black body radiation. But when the photons coming from the star, they pass through the molecular cloud, what we see is we start seeing absorption lines in the black body spectra. Okay, and these absorption lines are actually a characteristics of the particles, the molecules that may be present in this molecular cloud. One must remember that these molecular clouds are at very, very low temperatures. The densities are also not that much. The densities are much lower compared to the densities that we have here on Earth. Okay, so it is very, very difficult to actually create a lab environment and try to do this kind of measurement and reproduce the absorption spectra here on Earth. Okay, but experimentalists are doing good, and they have, I mean, they have gone to like few kelvins and they are able to measure, I mean, record these spectra. How do we see the spectra? The spectra can be seen using telescopes. So the telescope can be on the it may be a ground-based telescope, or it may be something. We have a SOFIA telescope which flies on an aircraft. We have ISO, which is Infrared Space Observatory, belongs to the European Space Agency, which is not working anymore. Recently, the JWST telescope was flown on December 25th, which is already in space and which will start observing within a couple of months. So, I mean, it is successfully launched, and we expect some very good results from that telescope. So coming to the molecules, so molecules, I mean, the bigger ones, I mean, the molecules that have 10 atoms or more. Okay, so all of them that have been detected in the interstellar space, they are organic, they have carbon. Okay, so and we also know that carbon is very, very important for life. Okay, so the life on Earth is all carbon based. If we have, apart from carbon, we have nitrogen, oxygen, and all these heavier elements that actually help in forming like all the organic stuff that we have in our bodies, or even the plants or animals. So this figure here shows the cycle that takes place in the interstellar environments. So most of these molecules are formed here in the circumstellar envelopes. So if we have a star, so we already know that, I mean, if I must tell you that most of the elements heavier than helium are formed inside stars. So be it carbon or oxygen or nitrogen, up to iron. All of these elements are formed inside stars, and then it is thrown away in the external environment of the star, and from there it goes to the interstellar space. Okay, so a lot of chemistry takes place in the circumstellar envelopes of evolved stars, and then it goes to the interstellar space, where the small molecules that have been formed in the circumstellar envelopes, they grow bigger and they form larger molecules, and then these molecules are part of the molecular clouds that I showed earlier, and they actually form new stars and new planets. So here we can see that a star is there, and we have a circumstellar disk. In this disk, there will be planets and asteroids and comets and all of the, like planetary system, all the bodies that belong to planetary system. Then again, the cycle goes on. Okay, so this is the this cycle of interstellar molecules. And then coming to organic chemistry, so one of the chemistry that takes place is in circumstellar envelope. The other chemistry takes place in the dense interstellar clouds, okay, which I've already shown. So in the so there a lot of molecules, complicated carbon-based molecules are being formed, which are difficult actually to, such chemistry is difficult to replicate here in our labs. Okay. And then one very important thing is that there are a lot of small molecules that actually are formed on dust surfaces. So what may happen is, like for example, the formation of hydrogen molecule H2. So one hydrogen gets adsorbed on the surface of a dust grain. The one more hydrogen actually sneaks in, and then it hops and comes close to the first hydrogen, and then it reacts and forms hydrogen molecule. The formation releases energy, which helps the hydrogen molecule to evaporate from the surface of the dust, and then it flies in the gas phase, and it flies in the interstellar medium. Okay, so this is what may happen actually, because the abundance of the hydrogen molecule in interstellar space, we are not able to explain it only on the basis of gas phase chemistry. So the chemistry that takes place on the dust surface is extremely important in this regard. So here you can see that a molecule gets adsorbed on the dust surface. There is another, an atom gets adsorbed on the dust surface. Another atom is sitting there. The first atom can, travel through the barrier via tunneling or hopping if it has enough energy, comes close to the first one, and then it reacts and it can evaporate. Okay, so and the dust grain actually helps in preserving the molecule as well. For example, here UV radiation from star is coming. If we have a H2 molecule here, which comes into direct contact of the photons, the UV photons, it can actually destroy the molecular bond, the bond between the two H atoms, and they can get separated. The molecule that is sitting on the other side of the dust grain, it is safe. Okay, and then it is preserved, and the dust grain is actually helping in preserving the molecules, and the dust grain also can help in formation of much larger, much complex molecules like water, methanol, ammonia, and even the ribose and DNA base, the DNA bases as well. Because the life on Earth, we still don't know how the life on Earth came into existence. So it is also speculated that some of these molecules must have come through meteorites or in some other form, and must have dropped on the Earth, and then life actually evolved from those molecules. So I'll be talking about the largest ones. So one of the family is PHs, which is nothing but benzene rings, which are joined together, and then you can create as big molecule as you want, like a graphene sheet. And then there are fullerenes. So fullerene C60, C70 have already been detected. So I'll talk about fullerenes first. So C60 and C70 have already been detected using their vibrational spectra in the circumstellar environment of a planetary nebula. So planetary nebula is a evolved star. The star is sitting at the center, and its circumstellar environment is slowly moving away from the star. So it looks like a planet. That is why it's called a planetary nebula. So in that particular environment, C60 and C70 have been detected. This environment is H deficient environment. So H atoms or H molecules are missing from this environment. That is why we do not see pH molecules. So the main difference between pH molecules and the fullerenes is that pH molecules on the sides, they have a lot of hydrogen atoms. Fullerenes do not. So if I explain the spectra here, so you'd see two intense lines, which is because of the radial motion. So in the radial motion means that the fullerene is, the buckyball is being compressed and it expands. So this is the radial motion. And these two lines here, the weaker ones, actually is because of the tangential vibrations. That means the surface is moving. The surface is not expanding in and out, but the surface is moving actually tangentially in a tangential direction. So those kind of vibrations lead to the weaker ones at 8.5 and 7 micron. This is the 8.5 band. This is the 7 micron band. And we have two bands here at about 17 micron and about 19 micron, which is due to the radial vibration in C60. Okay. So this is observations. This is plainly detected by Spitzer Space Telescope by Jan Kami, and this was published in Science. So here, this is Jan Kami holding his fullerene molecule. Now I come to diffuse interstellar bands. Diffuse interstellar bands, I mean, this figure here, this plot is between, you can say that it is absorption or intensity versus lambda inverse, 1 over lambda. And this is also known as the interstellar extinction curve. So how do we plot this? You have to collect photons coming from a star. The photons are actually passing through the interstellar environment, the interstellar space. So the photons actually, somewhere they are getting absorbed, somewhere they are getting scattered. So we say that the photons are getting extinct. Okay. So we see that because this is lambda inverse. So here we have the infrared, this is the visible region. And from here we have UV and far UV. So we see that the absorption is less. The scattering or the extinction of the photon is less in the IR region. But as we go towards the lower wavelength side, the UV, the visible UV and far UV, the extinction increases. Okay. Here on the interstellar extinction curve, we see a lot of lines. These are absorption lines, absorption features on the interstellar extinction curve. And these are about few hundreds, 300 to 400 absorption lines have been seen in the UV and the visible part. So this is the, I mean, this is the infrared, then we have visible and the UV. So most of the lines are in the visible part. There are few lines in the infrared and some in the UV as well. Okay. So these are known as diffuse interstellar bands. These are broad absorption features. And it is said that they are coming because of some carbon-based molecules, some large molecules, because they are broad. It is not coming from particulate matter, because particulate matter may also lead to polarization, but there is no polarization seen in these features. So, and a very nice experiment which was published in Nature by John Mayer and his group was done in Switzerland, University of Basel. And what he did, he tried to replicate the interstellar environment in his lab, and he measured the absorption spectra of C60 plus, okay, fullerene cation in gas phase. And these, all the dots that we see here in this plot are the lab results, and the two red lines are the two features, the two diffuse interstellar band features actually, which are coming from observations. Okay, and they perfectly match. So first time a lab report actually matched the diffuse interstellar bands. No other diffuse, I mean, there are 300-400 diffuse interstellar bands. Only 2 of these bands have been matched with a molecule. Okay, so this is the first report, and this diffuse interstellar bands were first reported about 100 years back in 1921 or 22. So this is like more than 100 years. The first time in 2015, they got a perfect match, and this actually corroborates with the detection of C60 in space. Okay, so the first time it was a concrete result showing that C60 plus is present in space. So how these C60 might be forming? So I'm giving one particular example where we start with a pH molecule, get rid of some of the carbon atoms. So the 6-membered ring are transformed to 5-membered rings. And when we have 5-membered rings, then the pH molecule, which is planar, actually starts curling up. When it starts curling up, it curls up like this, it forms a bowl, and then this may lead to the formation of buckyballs or fullerenes. Okay, so this kind of reaction is, proposed, occurs efficiently at about 1500 Kelvin. So this kind of temperatures exist in the external environments of stars. We cannot go very far from the star where it will be very, very cold, and these reactions will not occur. So in the planetary nebula kind of environment where C60 was detected, there we find such kind of temperatures and densities. Okay, coming to polycyclic aromatic hydrocarbons. So my PhD and a lot of work I have done on polycyclic aromatic hydrocarbon molecules. So what are these? These are basically fused benzene rings with a lot of hydrogens on the edges. And they are very, very stable because of the structure. The delocalized electrons makes it more stable. We need a very stable molecules because the interstellar space is very harsh. You have a lot of photons, high energy photons coming and hitting the molecules. So they should not be destroyed immediately. So that is why we need a lot of stable molecules. And these molecules may contain about 10% of the total carbon present in the universe. Okay, but they are highly carcinogenic. So pH molecules actually are very abundant in terrestrial environments on the Earth's surface. Whenever you burn a hydrocarbon, for example, paper, wood, anything, cigarette smoke, vehicle exhaust, they all contain pH molecules and soot. Okay, and they are highly carcinogenic. So whenever we are dealing with them, in labs, etc., we have to be very, very careful. So the main motivation to study pHs, I will be talking only about the astrophysical motivations. So the first one is the detection of unidentified infrared bands, which I'll be talking about in detail later. Then it is also said that these pH molecules may be responsible for this bump in the interstellar extinction curve. Then there is an extended red emission in the visible from some environments. It is seen that there is a big interstellar, extended red emission, which might be coming from pH clusters, and then diffuse interstellar bands. So we have seen that a couple of diffuse interstellar bands are explained by fullerene cations, but most of these remain unexplained. And it is said that some of these are coming because of pH molecules. But pH molecule is not a single molecule. It's a family, actually. It's a family. So that is why, focusing only on one molecule or trying to identify one individual pH molecule is very, very difficult, especially in interstellar environments. So unidentified infrared bands are nothing but vibrational features coming from the pH molecules. They were first observed in 1973, and the main features are at 3.3 microns, 6.2 microns, 7.7, 8.6, and 11.2 microns. So how these actually the features occur? So here, these were GIF images which are not working in the PDF file. So what may happen is a pH molecule may absorb a UV photon, and then it will get excited, something like this. This is for a cation. So it can get excited. Internal conversion may take place. It can go to a higher vibrational, energy level of a lower electronic level, and then it can come to again higher vibrational level of the lowest electronic level, and then through cascade kind of emission, it comes back to the lowest vibrational level. Okay, so all of these will lead to individual IR photons. So that is why the vibrational features of pH molecules are very, very strong. We see CH stretch We also see CC stretch and CH in plane bending and CH out of plane bending. So there are several mode of vibration present in a single pH molecule. A thing to remember is that the UIR bands, which are seen at 3.3, 6.2, 7.7, 8.6, and 11.2, the main ones, they are all found together. I mean, you look, if we see one particular UIR band, we will see all of them. Okay, and all of these are coming only, from a pH molecule. If so, other molecules, we might get the CC or CH stretch or CC stretch, but that other molecule will not be able to explain the presence of other UIR bands. But pH molecules are one class of molecules, one family of molecules that are able to explain all of the bands together. Okay, so here in this figure, we have shown the effect of ionization. So the red plot, the red line is because of large pHs, the vibrational spectra of large pHs, and the blue one is small pHs. So the top one is because of neutral pHs. This is due to the cation. So we see a lot of intensity changes, and we find that the spectra of pH cations actually match better with the observed features compared to the neutral molecules, because in the spectra of cations, the 6.2, 7.7, 8.6 are much stronger compared to the neutrals. In the neutrals, we have only the 3.3 micron or the CH stretch band and the CH out of plane band, which is at about 11.2 micron. Only two features are strong, while in the cations, we see that the 6.2, 7.7, 8.6, all of these are strong, which are strong in the observed spectra, while the weakest feature is the 3.3 micron, which actually is quite weak in the spectra of cations. So a lot of variation actually is seen in the UIR band spectra. So this variation is not only in terms of intensity, but in the position, the band position as well. So here, this figure clearly shows that we see the 6.2 micron, and when we go up, we see that the 6.2 micron shifts from 6.2 to about 6.3 micron. Okay, and same thing we can see in the 7.7 micron band. So here we see that 7.7 micron band has two actually bands. One is at 7.6 micron, one is at, the weaker one is at 7.8 micron. And when we move up, we see that there is only one P. Okay, so what is happening actually? So when we are going up, we are going from a very harsh interstellar environment to a benign environment, to a milder environment. Okay, same thing here also. We are going from a harsh interstellar environment to a mild environment. So shorter wavelengths are actually present in harsh environments, and the longer wavelengths are present in milder environments. So these variations in the pH, the variations in the position of the pH bands actually tells us about the environments, about the interstellar environment where they are present actually. So this is a very, very important information that we get from studying the variation in the band position of the interstellar pH molecules. So why the reason for variation is structural variation. So we can have linear pHs, we can have compact pHs, we can have very large pHs, substituted pHs. So what may happen is a carbon can be substituted by a nitrogen, one of the hydrogen can be replaced by a deuterium, and so on. And pHs with aliphatic groups, pHs with side chains. Okay, so some of them I'm going to discuss here. So here what is happening is we have a pH molecule, a big pH molecule with the and then the carbons are being replaced with nitrogen. So all these colored balls are nitrogen atoms, and one by one they are being replaced. If we replace the outermost carbon with a nitrogen, we see this is the CC stretch band at 6.2 microns. Okay, so what we see is the 6.2 micron band is shifting towards lower wavelength. Okay, so as we substitute, as we go deeper inside the pH molecule, we see that the 6.2 micron feature, which was at 6.3 micron, is shifting to 6.2. Actually, it is shifting to lower wavelengths when we go deep inside the pH molecule. Okay, so this is one explanation for the shifting of the bands. This work we recently, got published. So here what we have done is we have also studied the substitution of nitrogen inside the pH molecule. What the surprise result was that in the spectra of neutral nitrogen substituted pH molecule, we found that the 6.2 micron is as strong as was found in pH cation unsubstituted pH ionized pH molecule. Okay, so a neutral nitrogen substituted pH molecule also may be responsible for the 6.2 or 7.7 micron band. So this is a surprise result that we got here, which published this year itself. So here what we have studied is, here we have studied pH molecules with side chains. Side chains means we have aliphatic side chains. For example, we can attach CH4, we can replace one of the hydrogen on the outside of the pH with a CH4 or C2H5 or something like that. Okay, so that adds aliphatic group to the pH molecule. So apart from the 3.3 micron band, which is because of the aromatic CH stretch, we start getting aliphatic CH stretch as well, which is occurring at about 3.4 and 3.5 micron bands. So all these gray bands which you are seeing are the observed features, while our features are plotted. So the black one is the neutral and the red one is the cation. Some of them match very well with the observations, but others do not. Okay, so this actually is telling us about the variation in the band position. The effect of deuterium. Okay, so what we did was we did two things. One was replacing one of the hydrogen with deuterium. The other was that we add extra D here. So the hydrogen remains and we add extra D. Okay, so what we found was that if we have a D atom substituted, the CH stretch actually shifts to a longer wavelength here. Okay, so and here what we have is we have an extra H. So this makes this particular CH stretch aliphatic. So all of these are aromatic CH stretch, and we also have a aliphatic CH stretch. So this is the aliphatic CH stretch. And when we replace one of the H with D atom here, so we have aliphatic structure with CHD. Okay, so we also get CH stretch, we also get CD stretch. And CD stretch bands are already actually observed in the interstellar. They are very, very weak bands, but they have already been detected using telescope observations at about 4.4 microns and 4.6 microns. So they have already been detected, and we are able to explain by substituting with deuterium the observed features. Okay, so this probably is my last slide, which explains how small molecules are formed in the circumstellar envelopes of carbon-rich stars, and when they move away from the circumstellar environment, they move in the interstellar space. These molecules are getting converted to larger molecules. The interstellar space may have a variety of molecules. Okay, so they might have pHs, they will have fullerenes, they also might have carbon nanotubes, they have onion shell like structures, they have soot like structures. Okay, so nanomaterial like structures, something like this. Okay, so all of this kind of molecules are possible in the interstellar medium. We still have not detected most of these, but because the reaction, the modeling on actually shows that the formation is actually likely, to be happening in interstellar environments, considering the densities and the temperature. So we see that here the variation of the density actually. So the density in the circumstellar envelope is about 10 to the 18 cc's, and when we go to interstellar space, it is only about 10 to the 5 to 10 to the 3 per centimeter cube number of particles. Okay, so when we go to the less dense environments, we find larger molecules. So just to summarize, the large molecules actually help in maintaining a lot of physical properties of the interstellar medium. For example, the charge, because they are also present in ionized states. So the electron which is removed from the molecule actually travels, it is free in the interstellar space. So it maintains the charge, it also maintains the chemistry, the energetics of the interstellar environment. The spectra of these molecules reveal about the environments, the physical properties of the environment. Okay, so this is very important. So if we are able to measure the intensity variations and the variation in the band position, we actually get a lot of information about the environment where these molecules may be present. And JWST, which was recently launched, will be telling us a lot about these molecules and interstellar environments. So I'd like to stop here. Thank you very much. I'll appreciate if you have any questions or comments on my presentation. Thank you very much.
Thank you, Dr. Amit, for a very nice presentation on the formation and detection and existence of organics in the interstellar medium and space. Thanks for giving the picture of this. I wonder, so any questions from the audience? Okay, so if there are no further questions, we will move ahead with our next speaker of the session, Dr. Sanchita Roy. She is an assistant professor and HOD of Department of Physics, University of Science and Technology in Meghalaya. Her research interest is on investigating small particles of different origin by using light scattering techniques, design, fabrication, and development of novel instruments for optical measurements and characterization of particulate matters, data analysis using scattering theories and simulation. I welcome Dr. Sanchita for her talk.
Thank you, Dr. Sritama, for your introduction. And first of all, I would like to thank the organizers of the International Conference on Convergence of Interdisciplinary Science 2022. And it is indeed a very good platform, actually, to gather knowledge. So today I'll be presenting my work, and let me share my screen. Dr. Sritama, is it visible?
Yes, your slide is visible, but you are yet to put it in the slideshow mode, I guess.
Yes, yes. Is it okay now?
Yeah, that's perfect. Yeah.
Okay. So the title of my presentation is Static Light Scattering Tool for Morphological Quantification of Bioparticles. So it's a part of the biophotonic applications, actually, which we are, investigating in our present work. So some of the outline, which I'll skip, and to start with, actually, light scattering is a very important technique, and we know that light is scattered by almost every object in this universe, and yet it's a very interesting phenomena, because like scattering is actually a phenomena when energy of some form, it is deviated to move from its straight path due to the presence of some non-uniformities in the medium through which it passes. So what happens is the incoming electromagnetic wave, which interacts with the scattering particle, it induces a dipole moment. And this oscillating dipole moment, actually, it is re-radiated and it gets encoded with different informations of the scattering particle. So in view of the biological or biosciences application, when we speak about light scattering, it is an indestructible and non-invasive technique, because Usually, biochemical methods are used for the characterization of particles, which sometimes destroys the particle, the morphology of the particle. But when we use this light scattering tool, so it is non-destructive, it is non-invasive, and yet an efficient tool for characterizing the morphology of different biological particles. Now, there are some known particles which has been characterized by different biochemical methods, but there are many particles which are yet to be explored. Keeping in view of the present scenario, like every day we are we are getting the news of some of the new variants of the coronavirus, and direct I mean investigation on these particles, like it is not possible always by experimentation, because it requires high biosafety techniques or biosafety to be maintained in the laboratory conditions. So in such cases, like if we have to take example of today's scenario, light scattering technique can prove to be a very important and tool for investigating such particles and development of some biosensors. So this was some introductory note about the importance of light scattering. And usually May theory and the T matrix are commonly used for the spherical and non-spherical particles for investigation. Now, this is what I was talking about, that it is a very fundamental thing, but since some students also might be the participant and the researchers, so it's the electromagnetic wave which interacts with the particle, and then it induces the dipole moment, and this oscillating dipole moment is re-radiated in the form of scattered wave, and it gets encoded with different information. So what kind of information it gets encoded with, we'll be discussing. This is a typical light scattering instrument which is usually used. So it's only a schematic layout of an instrument, and different researchers have been using this kind of instrument, and they have also improvised upon the versions as per the requirement and dependency on the type of the scattering particles they investigate. So it makes use of a laser light as a probe, and then you can see a beam splitter and delivering optics where the linear polarizers or circular polarizers, these are used, and then this light, it is incident on the scattering particle, which scatters the incident light in different direction, and the detector, it collects this signal. It is interfaced to a system and to a data acquisition system, and which collects and stores all the information of the scattered signal. Now, static light scattering, as my title slide, it included that it is static light scattering. There are two approaches, like we can investigate using the static light scattering or the dynamic light scattering. So here, static light scattering, actually, it is a measurement of the scattered intensity of light. As you see here, it will collect the scattered intensity of light as a measure of the angular distance. So as a measure of this angular distance, so as the detector rotates, say from an angle of 10 degrees to 170 degrees, it will collect all the information of the scattered signal, and this will be used to interpret the results. So now there are theoretical approach also. So basically, the polarization state of the scattered light, it is related to the polarization state of the incident light by a 4x4 matrix called the Mueller matrix. So as I have shown in the schematic layout of the scattering instrument, so the light can get polarized by the use of some optical components, the polarizers and all. So here, the parameters IS, QS, US, VS are the Stokes parameters of the scattered light, which is related to the Stokes parameters of the incident light by a 4x4 matrix, and it is a popular and very important matrix called the Mueller matrix. So we are actually we are focusing on the first two elements like this of the Mueller matrix, that is A11 and A12, from which we are going to find out the volume scattering function beta theta and the degree of linear polarization. So this will carry information about the first element of the matrix, that is A11. It carries information about the size of the particle. So here we can see the interpretation of the different matrix elements, where we are focusing on the A11 and A12. So it is transformation of total intensity of incident light. Basically, we get this information about general size, and the element A12, it gives information about the size, shape, etc. So now there are two approaches. Either one can work with the experimentation and or theoretical, or both, to make a comparative analysis for the validation of the observations and results. Some important theories of light scattering which are being widely used is highlighted here, out of which we have made use of the May theory rather, and the T matrix method. So the May theory is used mainly for the spherical particles. So if our scatterers or the particles under investigations are spherical, so we make use of this theory. And T matrix method is used usually for the non-spherical particles which are randomly oriented. So these are the theoretical approach of investigating the particles using light scattering method. Now, we have investigated on different particles, but few results only we are going to share in this presentation because of the constraint of time. So E. coli, as we know, it is a bacteria. So it is a gram-negative bacteria, and it is rod-shaped. And we know that it plays an important role to enable the rapid continuous production and purification in large amount of humans. So in biological sciences like E. coli, it holds important. Usually it is not very harmful, but it can cause severe disease sometimes by a particular strain. So in fact, knowing the scattering from each type of strain is also very important. So the scattering profile which we can obtain from different strain is also a database for knowing like which spreads more or which is more contagious than any other E. coli strain. So the culture was done in the Department of Biotechnology, and here I do not want to discuss more. So our main purpose is the collection of the E. coli sample after the culture, and the scanning electron micrograph image of these E. coli cells is displayed here, and it shows a spheroidal kind of structure. And here, from this SEM image, why it is important? Because we come to know about the size distribution of the particles, bioparticles. So size distribution is very important parameter actually, because we incorporate this into the theoretical program to generate the scattering profile. So the size distribution profile of these particles, it shows a Gaussian pattern, and we see that like one size is dominated. We find more number of size. Of this, particle equivalent particle radius. So here the unit is missed. Actually, it is micrometer. So so this particular size is taken as the model radius, and the model radius is incorporated into the theoretical program. Now, another important aspect, like it is the absorption UV visible spectroscopic result, and it is important keeping in view to find the non-resonant absorbance. Since I said that we use a laser light, so the choice of the wavelength of light which we take. So here we are interested for the non-resonant absorbance. So it is around like the red 632.8 nanometer is the non-resonant wavelength. So we select that wavelength, and that is also an important parameter which we incorporate in our theoretical program. Again, another important aspect is the purity of the samples which we are investigating. So the EDX analysis, it allows to find out the composition of the strain of the biological species, and from which we can ensure the purity of the sample what we are investigating. So now the parameters which are used in order to generate the theoretical graph. So these are the parameters, and from where we could find out the volume scattering function. So as I have said that the volume scattering function beta theta, it is actually expressed as this one. So A11, so it is like it is dependent upon A11. So if we can find out experimentally also this A11, or theoretically we can find by using the the scattering theories or the standard open source code. So the volume scattering function, which of this sample of E. coli, we used both the theories, the me plot, which is usually used for the spherical particles, as well as T matrix. Now here, as I have mentioned that me theory is used for the spherical particles, here we see that all the particles are not spherical. They are rather, elongated. They are spheroidal. But here we have, I must mention that me theory can also be used for the randomly oriented particle, which may be non-spherical also. But if the particles are aligned, then we must use the T matrix method. However, both these theories have proved to be good enough for the characterization. So as we see that me theory and T matrix plot, they show a forward scattering lobe, and they follow the same pattern. However, there is a difference. So this difference in both the plots, it points out the importance of using a particular theory for the characterization of the particle. So what I mean is, even if the particles are non-spherical, and it is considered that we can use the me theory for the non-spherical but randomly oriented particle, but then it is very important for the choice of proper theory to quantify the results. So these are the established results for the E. coli particle, which gives information about the general size of the particle, and it is the degree of linear polarization, so which depends upon the parallel intensity of light and the perpendicular intensity of the light. So that we get the information of the degree of linear polarization. So from here, the important finding is this, that both the beta theta and p theta, it depends upon the size distribution or the density of the particles present. And here I must mention that the particles are they are monodispersed, and we take into account the single scattering. So beta theta and p theta depends upon the T matrix and me plot, which exhibits forward scattering. However, some significant observations we have found for the same bacterial strain, but we have found significant results using both the theories. Now another important work which we took up, as experimentation is not possible now, but in future we wish to work with the experimental approach also. So another particle which we investigated is the coronavirus, SARS-CoV-2. So it is a very well-known fact that since year 2019, there has been outbreak of this virus, and it has caused a havoc throughout the globe, and extensive research work is being carried out now in order to find different information about these viruses. So in March 2003, it was first discovered. However, it's I mean it is known to all of us now during the present time. So these viruses, actually direct experimentation with these viruses is very difficult, as I have said. So there lies the importance of a light scattering technique to investigate on these particles, or we can say that the different types of the coronavirus, I mean different types, which I mean Omicron or whatever, Delta variant, Delta Cron is also coming up nowadays. So if we can know about the morphology from the scanning electron micrograph image, collect some information and use those parameters into a program, theoretical program, we can find out the scattering profiles of those particles. And if we can carry out experimentation, then we can find a correlation by making a comparative analysis, and we can I mean think of some interesting results which can possibly allow us to develop some biosensors for arresting this kind of pathogenic spread in the environment. Now, the viruses was these viruses was chosen, and usually it has a size which range, I'm sorry, it become range, so ranges from 80 nanometer to 120 nanometer. It has spikes in its body, so which forms an envelope kind of thing around the coronaviruses, and there is a narrow size distribution which we will see from the image which we have collected from some internet sources. And we investigated basically on the S11 and S12 element, and here we have presented the results of S11 element of the Mueller matrix. Now, this is a SEM image of the coronavirus, so collected from two different sources. Figure 1b, actually this image has been used by different researchers to model the particle or collect some carry out some research work in different aspects. So we have also used it as a standard image in our work. And the other one, here you can see figure 1b has a narrow size distribution. However, in figure 1a, there is a comparatively greater size distribution. As we can see, the arrow marks which points towards the presence of different size in the sample. So this is an image. It is an like animated image of the coronavirus, and which looks like the corona of the sun. So here the spikes actually. I would like to mention here that usually the biomolecules, the bioparticles, they have chirality. So it means that there is a left-handed image and there is a right-handed image. So it is something kind of a mirror image. So these molecules, if like usually, these molecules, even if we rotate it, so it will not bring back to the same particle because they are mirror images. So now the interesting thing is that the proteins, amino acids, or the nucleic acids, usually they are chiral. So now, as we have investigated here the S11 molecules, the A11 element, which I have shown, the A14 and A41 element of the Mueller matrix. So these elements, quickly I will go through this one. So this A14, this one, it actually, you can see that the circular intensity differential scattering. So if we can find out a ratio of this one, we can get information about the morphological information about the scatterer. So now we have started working with the first element itself, and we would like to extend our work to find the other elements. Now, since they are chiral, so they will always show unique scattering profile for each coronavirus or virion. Now, the protein, this viral protein, the viral protein is very important. Important in the sense that important information about this is very important, as the viral protein usually it binds with the porphyrin in the human body. So what is porphyrin? It consists of a 5-membered closed structure, which is containing 1 nitrogen and 4 carbon atoms. And this porphyrin in human body, it is mainly stored in the hemoglobin in form of heme. So the virus gets attracted to this, porphyrin. So it requires adequate amount of porphyrin, and thus it targets the hemoglobin. So this hemoglobin, it dissociates the iron to form porphyrin. So now this porphyrin is of interest of the virion. So what I mean is the presence of number of spikes in the particle, in the bioparticle, is very important, because the more spikes it is present in the bioparticle, the chances of binding it to the host cell becomes more. So that is why, investigations have been carried out based on light scattering for the particles for this kind of coronavirus. However, like we have started working or simulating rather in taking into account, the modeling, keeping in mind the number of spikes of this kind of particle. So what we are interested is that without the spike, how the particle will scatter, and to find information of all the matrix elements, and then decrease in number of spike or increase in number of spike, how the scattering profile changes. So these are the, as I have mentioned before, some the important parameters obtained from the size distribution of both the SEM images. And we here find the scattering profile of the coronavirus sample at a wavelength of 632.8 nanometer. So these are, information which we get by using Mee theory, as the particles are spherical. So what we find that one time we take the particles having a radius 175 nanometer with spikes, and without the spikes, it comes out to be this. So it is usually 2 different sizes only. So here when we are generating the scattering profile, so we are with spike and without spike. So it is kind of the envelope which we are taking into account, and one time we are not taking into account that spike envelope. And these are the distinct profiles which we get when we are taking out. So this is for the sample 1. Sample 1, as we have seen that it has a distribution. So we took into account all the radius, and along with the model radius also. So these are the distinct profile of the coronavirus for the S11 element, or rather here we are presenting the volume scattering function. So it is this one. So now model radius, we found it to be 125 nanometer. So now we come next to the modeling of this virus. So that one was this result is by simply using the Mee theory and generating the profile. Now we have also modeled this one. We simulated here, and as I have mentioned, we are presenting our work of S11 element here. So the simulation program, how the technique, it involves the distribution of the photons mainly in the program according to the density. So density means density of the spikes. So number of spikes, suppose we take number of spikes to be 50 or number of spikes to be 100, and not taking the number of spikes into account at all. So this one, so by modeling, we simulated the scattering profile at this, and this is the distinctive scattering profile of the coronavirus of sample 1. Now the comparison with the simulated and the theoretical, if we see, the simulated one is exhibited by the green scattering profile here. So we can see a similar pattern is followed here. So till around 65 to 70 degrees, we find a greater correlation, and beyond that there is a kind of deviation, so and which forms the distinctness of the profiles. So here simulated one, so we see that there is an agreement yet there is a deviation. Agreement means if we can see the pattern. So now we have to investigate further that, it shows, closer, resemblance with the spikes, with those particles having spikes at 125 nanometer or 100 nanometer rather than with 175 nanometer. So simulated one which was using the model radius, and this is the interesting result, that number of spikes, presence of spikes, it distinguishes that one with the model radius when we consider. So again, for the sample 2 also we found two different sizes which were very close. So we didn't have, we had an ignorable size distribution. But even though it was ignorable, we found distinct profile considering the spikes and without the spikes in these two different sizes. And again, this was simulated and the comparison shows this one. So we see that simulation modeling also, apart from this also, the use of me theory, we can use other theory also in our program to find a correlation with the observed results by me theory or T matrix or experimental results. So we can actually get more information if we can carry out real experimentation, work out with the first element, and then extend our work with the other elements of the matrix, so that we can correlate the experimental result with the simulated and the theoretical result. So this will enable us to get the morphological quantification of such kind of particle. So this is the importance of the work, and we are working on the degree of linear polarization and other elements as well. And we wish to work in the experimental aspects as well. So these are some results which are, the results which was observed. And the conclusion part, it's a general conclusion. Rather than being very specific. So it is like the importance of light scattering actually in investigating the bioparticles. So both in situ and ex situ, and which is an alternative means of investigation other than the biochemical methods which are being used in the laboratory. So simulation is a very important aspect, as it also gives information about the morphology of such kind of particles. So our results may be significant for comparative analysis with the experimental results for further validation, and we can use our code for such similar particles. So not only the coronavirus particles, but other particles as well. So some references, and I thank everyone for your patient hearing. Thank you.
Thank you, Dr. Sanchita, for a very enlightening talk and an important research on SARS-CoV-2 virus. I would like to ask our audience if anybody has any questions. Well, everything seems to be very clear to everyone. So moving on to the next and the last talk of the conference, I would like to invite Dr. Papia Roy. She is involved in a consultancy role with the Convention of Biological Diversity with the United Nations Environmental Programme Office in Montreal, Canada. She holds a PhD in environmental science from IIT ISM Dhanbad and has acquired global acknowledged credentials as a subject specialist for climate change policy and practice from the University of Toronto, Canada. So I would like to invite Dr. Papia Roy.
Okay, good afternoon or good morning or good evening, wherever you are. It's morning from me. Am I audible?
Yes.
To the next side. So, okay, let me start my screen sharing. Could you see it, please?
No, the slide has not appeared yet.
Oh, okay, wait. I think we need, all right.
I think it's coming. Yeah, the slide has come. You just need to do it slideshow mode.
Yeah, wait a second. Yes. All right.
Yeah, perfect.
All right. Thank you. So today, as per the last topic, it's like the environmental issues in our contemporary research of physics and engineering. I'll be talking about how the issues are involved in and why it has got its importance and why the science research nowadays is moving on to that direction. All right. Dr. Sritoma has already introduced me, so I'll avoid that part of introduction. However, today's journey, I will start with from the very ancient age of our time, not like the real primates time, but quite primitive one. And as you could guess, yes, nothing is there, but yes, we are going to start from the Stone Age. So this was the time where we say that human brains were quite developed, and we were coming out with the thought of some kind of innovations. And we could see all these pictures. We are making some kind of stone equipments for our regular survival. And that was the time when the innovation in science and engineering has started. And it merely was driven by the curiosity to find something rather than any other aspect of it. And it never stops, basically. Human inventions for the science and technology, it has never stopped. And I like to highlight some of it because we have done millions of technological invention over the years. This is like a million years ago when we started with the fire. We first did it. And then we started finding the wheels, which is like our entire civilization is running on it. It gives us the mobility. And it's unbelievably, it is nearly 600 BC, before the Christ. We found a static electricity also around the same time. And to quite unbelievable and shocking for many of you might be, because the balloon, what we see, and it was existed way before Christ was born, like nearly 200 BC. The hot air balloon in Peruvian culture are there. This one is my quite favorite. This is also like 200 BC. As you could see, the magnetic compass, and the Chinese have come up with this. And then we move on to the AD era, and there are lot progress were happening. And one of it was like the Gutenberg's printing machine, as you could see, and definitely a microscope. And there are many more. And who doesn't know the great invention of the steam engine, which probably pushed us even further and faster the way we innovate or look into the things. And it never stopped with this steam engine, and we aggressively moved forward. And as a result, we have like the nuclear reactors, right? We were able to build up our first atom bomb way before the World War. Then it came to computer era, which we cannot survive nowadays without about it. And nowadays we are talking about the artificial intelligence technologies, right? So human brains are constantly developing a lot of things which are useful always and supporting. But from this point, I once again like to go back to a little bit of ancient time. This is the picture. we would like to talk about the consequences when we just answer our curiosity without thinking where it is leading to us. This is a picture around 18th century in London. As you could see, the horse chariots are on the streets. London was quite prosperous. Can anybody imagine what kind of problem might have happened because of so many horse chariots in the street? It's quite eco-friendly technology. We are not using any fossil fuel, and there is no electricity, so we are not burning anyway. So what kind of consequences might have faced by that time? Any idea? Any wild case is welcome. Anybody? Any guess? Okay, I'm assuming people are thinking deeply, but let's move on. Unbelievably, the crisis happened with management of horse manure. Can you believe it? And this has resulted in the era of like great horse manure crisis in 1894 in London. And definitely this leads to another innovation of the motor car, but this was like a historically first incident, people say, where we didn't think about when we did something, how it is going to affect us or how we are going to address that issue. We had no answers. And it has the conventions on to how to manage this manure, but the answer was no. Okay, let's look into the next one. Oh my God, why it is not moving? Excuse me. All right. As the picture says, you know, this is the great atom bomb, which we dropped in Japan during the Second World War. Now, the consequences, I know you all have seen like the health issues, radioactive materials on the ground, but let's talk about in terms of money, because we understand that is better, the loss and the profit. So making this atom bomb, the Manhattan Project in US, it cost them $2 billion, right, at that time. And post-World War II, to incurring the recovery or the health cost for Japan was $20 billion, which is like a 10 times how much we invested on the bomb. Let's go to another one. This is a gray one. I personally like it because it was when I was young, this thing came into our environment, right? And I remember my my father told us, so look at the thing, it's so nice. It's waterproof, you have no issues, you can clean it up. And yes, that one is a really, really great. And we used it. And if I correctly remember, that's the time in end of 19th centuries that like a lot of industries move on to the production of plastic, right? And let's look onto the consequences. Number one, this is one biggest dump yard, and I have worked in one of the major dumping ground in Bangalore. In 2014, there was a massive protest by the villagers. And this is, you could just see the one part of the dump yard, whereas the area that covers it is 64-hectare prime land, right? And it's just not only the dump of the plastics or this one. It has the further consequences which nobody evaluated, and that's why the protest was, because it's an outskirts of the city, a kind of village, and people use the drinking water from the groundwater source. What has happened after 2-3 years, because of the leachate problem, the whole water get contaminated or polluted, and so the water that is coming out from the tube, it is black in color. And we are not just at the dump, we are just even harming the other animal. Even being a rational, most intelligent animal, we are harming the others too. Let's look at this, the poor turtle. Despite of having two prominent hands, kind of like us, but it died because of the plastic choking. And I know you have seen many other disturbing pictures. This is just one of the representation. Let's look onto this, the fridge. It reminds us many important things. We find the great invention, definitely. We could stop perishing our food. We can keep it longer. If you like Coke and Pepsi, yes, the chilled one, we can get it. But as you think, yes, finally we'll end up ourselves into another big problem of the ozone depletion. This is a picture from the United Nations Ozone Secretariat, a 3D model scientists developed. It was like a 1980, around 80 to 85. And this blue patch, the entire blue patch, what you could see is the hole that was generated at that time. And it is the only because of the use of chlorofluorocarbon, which we use it as a cooling agent for the refrigerator, right? This was a kind of landmark moment for environment. And the last one, I mean, there are many more, but I would like to stop here with this. As I said, the horse chariot pushed us further, and necessity is the mother of invention, and we went to the motor vehicle, and it goes on, right? And now we are struggling with this global temperature rise because the amount of carbon dioxide pumped into transport sector alone, it is nearly 25%, right? And now we are struggling how to manage it well below the 1.2 degree average temperature rise globally. Okay, now before moving to the next part, I would like to say that United Nations were existing post-World War, but that time their main role was more of a to the Refugee Council peacekeeping activity. But it was 1980 because of the some people become really vocal that we need to address quite a lot of issues globally. And that's the time that United Nations spreaded its wings further, and it established other agencies under that who just not only look for the refugee or the peacekeeping mission, but also to the wholesome environment. And it is at the point we defined environment just not as like a trees or biodiversity. It started including the social dimension, even including the poverty, natural disaster, everything is incorporated. And accordingly, they developed 25,000, nearly 25,000 NGOs in the late 19th century. Last century. So let's look at that. The refrigerator issue is like the one major issue that pushed the entire world to come into the consensus. And this was like a first concerted effort in Montreal Protocol where 197 countries participated in addressing this ozone hole. This was a very successful treaty so far in related to environment. And this is the time when also people realize about the load of carbon dioxide, greenhouse effect, and global warming. And as a need of hour, they established IPCC, Intergovernmental Panel on Climate Change. So this is an organization under United Nations which works on so far the biggest event in the history of environment is the climate change, right? And nearly 800 scientists those are working for the biophysical part of IPCC's report. There are nearly 650 social scientists and economists. They are working for the policy development, the road ahead to design on it. Here is a very small video regarding the latest IPCC's development, and let's have a look.
Papiya, does the video has any audio as well?
Is it not playing? I mean, I could hear it.
No, the audio is not coming to us.
Okay. Is there any? I'm so sorry. Is this? A video doesn't have any talk though. Most of them are with the music and the lines. What you
Okay.
could see.
Yeah.
Yeah, I think let's just play it.
Yeah. Okay.
Is it visible?
It's not playing yet, I guess. Yeah,
Yep.
it is visible.
Okay.
Yeah.
Thank you. As you could see in most of the studies, it's way beyond the science. Like it has the hardcore science, definitely. The projections modeling, which are like the physics and biochemistry people are doing relentlessly over the few years. But it also has many things to do by like the social scientists for this rehabilitation of the people, and there are a lot of displacement and identifying weather and climate events. So meteorologists also playing a very crucial role in this entire thing. Biological science is very strong in any IPCC's report, because anything that has to do is the natural resources that our life thrives on, right? So it ends by saying like our climate is our future. As you all know, the entire human civilization is very much threatened by with the presence of climate change, which is like the people of different sectors, different areas are working together to address these issues. Now, the climate crisis, when we look onto it, it is a very global phenomena. And that's the point. People become very conscientious, people become active to do something. Although the phenomena is quite global, the problem is it is affecting the local, right? And you look at the centerpiece of this slide, where we are talking about the natural disaster. Anytime the disaster is happening, which is impacting more in the two important components, the economy of that country or the region and the natural resources. And once these two get imbalanced, surprisingly, it affects every area of our society. Look at the food crisis, it affects the food, it affects the job, it affects the human health. On the other side, this leads to the climate migration and the access to energy. People are devoid of energy. And then the last one is the poverty. Right. I would like to share one point, like 10 years before, when I met one very prominent economist from London School of Economics. The question we asked, like, what do you think that the climate change will lead us? And he says, as an economist point of view or economical point of view, he says he's more worried about the climate migrant because of this global crisis. And today the whole world is making a hue and cry about this climate immigrant because of the natural disasters. Now, this is another area under this whole lot of environment and social science, the new hit pandemic. You won't believe in the first IPCC, not the first, the second or third IPCC's report in the early, before 2010, the report clearly says the major consequences, one of the major consequences climate change is going to have the new diseases which are unknown, right? And we could see the corona is kind of like a very new, and it has no ways a genetical mutation that pre-existed. Because of the changing of the whole environmental system, it is supporting that virus to grow and taking a different direction. Now, when we look into the pandemic, what we definitely need a lot of doctors and research and development, of course, for the medicine and protection of the people. We also need the technology. So there is a role to play. As we see, the whole conference, we are doing it virtually, and the whole office system is now today moved into the virtual system. But there are two more identified sectors which are playing a major role, because the post-pandemic recovery, we need the economics for financial planning, how the funding should flow to, let's say, reconcile or restructure a country's economy, the recovery of a country. And we need a clear policy roadmap, because ultimately these policies will lay down the foundation how to walk into the road ahead after the post-pandemic. So nowadays the science is just not limited into the physics, engineering, chemistry, biology. Social scientists, economists, policymakers, and too surprisingly, even the bureaucrats have a defined role, a huge role to play in this area. These are the four major things nowadays we are talking about in future, which is going to come, and we are more focusing on it. Access to the clean energy for the entire globe. Now, the clean energy means we are clearly moving out of the fossil fuel. Now, what are the options? Yes, we have the solar, we have the water, those natural resources, but to optimize it, or just not to create another crisis like horse manure in 1894, we need a clear direction, what kind of materials we should use, and what should we do, whom should we target to do this, and the policy and the funding opportunities for implementing these things in future. So everybody has a role to play to address this global crisis. We are also talking about the green transportation. So the whole transportation sector is going to revamp. It's from motor designing to the fuel and the efficiency, of course, we were going to talk about. And then we have the resilient infrastructure. This is the very new component has been emerged in 2020, when the entire globe started talking about the resilient infrastructure. Just it's not resilient only to the climate change or the environmental issue, but this also has a very three core social dimension. It should be the resilient infrastructure, means it should include the poverty reduction. It should include the longevity of the infrastructure, and also the building materials it is started talking about, which are suitable, which is not environmentally harmful, and also the plan which should talks about the end of product use, which is very, very important. Basically, it is incorporating the life cycle approach, and the whole globe is pushing forward to every country to adopt this resilient infrastructure setup in their environmental clearance process, which is kind of like a big challenge. And especially it's a big challenge the countries like Southeast Asia, like India, like us, where we always have different priorities before addressing the environmental issues. And one very important thing, as you know, our civilization entirely thrives on the natural resources, and we exploited it to some extent that we didn't care because we wanted to grow. This is another new arena from 2022. This global biodiversity and natural resource accounting is going to come into our sector of GDP. From my experience, I would like to share a point here. Natural resource accounting is not a very new thing. People have tried, attempted, and failed. Although World Bank has a very clear methodology how to achieve it, but it couldn't reach to that point. And once we calculate, surprisingly, most of the countries, it's like 98% of the countries fail to achieve the higher GDP when they are incorporating the natural resources. So as you could see, there is a clear role to play the social scientist or environmental scientist in this work. Considering all this, I think you are quite familiar of the Sustainable Development Goals of United Nations, and you see we have a 17 targeted goals which talks just not the climate, but about the gender, clean water, industries, poverty, education. And to achieve these 17 goals, we have nearly 149 targets, and people are struggling. So it's not just the one issue which should be addressed. There are many, many issues which are just cross-cutting each other. And that's why the transdisciplinary research or science is becoming more and more popular nowadays. And the good thing is what I could see, a whole lot of funding opportunities is moving from the traditional science to the transdisciplinary science, which is quite amazing. So when you look onto the convergence of science, you see I put that best logo in the center. It's like a ribbons, it's just overlapping each other. We need scientists, definitely. Even for this global crisis, as I mentioned you, 800 scientists across the globe are working for the climate change consequences. We have the engineers who are working relentlessly for the innovations. And there are the social scientists who are providing the direction which we should move with our innovation. We cannot ignore the presence of economists in this whole part, because the entire financial flow or the finance, how to tax, how to take out the money, and how to roll on the projects in future, they have a bigger role to play. We need the clear policy direction to guide our final bureaucrats. I know many of us, we don't like to talk about them, neither me, but as a country's head, these are the people who will kickstart with something rolling out for the people. So it's a very, very important part of this entire community. As Dr. Sritama says, you cannot hear the video voice. What I'm going to do is I'll just play it from here, one last video. Dr. Sritama, could you just say you can see it and hear it?
It is starting, yeah, but
could you
again,
hear the voice?
No, there is no audio to it that we can hear.
I'm so sorry. I just don't know how to fix this.
I think it's coming as some subtitle or something. I mean,
yes,
I
it
think
is
that should
coming as a
be,
subtitles.
yeah, that should be good for us. If it is a bit longer video, then maybe I can suggest you to summarize it to us, because
Oh
we
yeah,
are
sure.
kind of
So this
slightly
is
overshooting the time.
basically the video which is talking about the importance of the transdisciplinary science. And as you could see, Mr. John is working for the climate migrants. And we have, I'll just move forward a little bit. This lady from our India, she's working one of the cooling part of these goals, like as you could see, is the global cooling demand, how she is understanding, addressing the sustainable development for this. She's from the Smith School of Enterprise and Environment, and they are working into the technologies, how the product could be made, where it could be developed, where it could be the end product, the entire life cycle for it. And I think I will just share the link if you would like to watch
Yes,
the
yes,
entire.
that
Yeah,
will be
that would be
great.
great,
Yeah.
actually.
Yeah.
And right. All right. And I'm almost at the end of my slide. Sorry. So I would like to end my slide as the same way, like how the dinosaur is saying, don't choose extinction. This is a very important message and we are spreading as part of the United Nations from 2021, where a dinosaur is coming into the climate conference and saying, see, look at a lot of damages you have already done, but you still have a chance to do something, to reverse, to hold, and to control. So don't choose your own extinction. So as you could see, the YouTube link is there. So those who will be interested, you can definitely check on it. It's very interesting and it's very funny, but at the
You
same time,
can
very
post
thought-provoking.
the link videos in our chat. Maybe it will be easy for us to just.
Yeah, sure.
Yeah.
Right. So thank you everyone for accommodating me at this time at the end of conference. Did I stop sharing my screen? I guess yes.
Yeah. Thank you, Papia, so much for this very crucial and critical presentation on one of the most important topics, which is environmental science, and it is an ultimate topic to witness confluence of various streams and the interdisciplinary science, which is the very target of this conference. Thank you for such a nice presentation.
Thank you so much.
So we come to almost towards the end of this session, and which I would like to end again by summarizing the session. So we will go through what we actually heard from various speakers. So Dr. Arup, he talked about the two-phase flow, its basics, and the techniques of images and signal processing, and various probes of conductivity, processing circuit, single sensor for sensing simultaneous flow of two immiscible liquids. After which we went to the second talk of the day of this session. So it was about polyaromatic hydrocarbons in interstellar medium, and Dr. Amit talked about how these organics get formed and how they are detected using infrared spectroscopy, and his research on the substituted PAHs. Then the third talk today, it talked about Dr. Sanchita talked about the light scattering instrument, the scattering matrix element, and the interpretation and theory for detailed analysis of E. coli, and her research on understanding the SARS-CoV-2 virus better. And coming to the last talk of this session, Dr. Papia talked about the global environmental issues originating due to various anthropogenic activities and the various conventions to protect the natural resources and the solutions which are proposed in terms of improving energy, transportation, infrastructure, and biodiversity and the natural resources. So with this, I kind of tried to briefly summarize what we heard, and yeah, I must say that the session actually witnessed a proper interdisciplinary talks going on and the researches which are being done. And so with this, we come to the end of the talk sessions. So after this, I have an announcement to make. So with the permission of the judges and the organizing committee, I think I have the results for the poster presentation sessions. So as I got to know from the judges, there were 5 judges for judging the posters, and as I got to know from them, it was a very tough and tight competition between the speakers, and from there we could have our winners. So the winner or the first prize goes to Arijit Jana, uh, who will be receiving a prize worth 5,000 INR, and then there was a tie between the second winners or the runners up. So there are 2 people, Dr. Shubhankar Chakravarti and Pratik Boga. Both of them have tied, and they get the second prize worth 3,000 INR.
Let's congratulate them.
Congratulations
let's
to
have
the winners. Saurabh,
please do some.
Saurabh, are you saying something?
Yes, do clap to the.
Yes, please. We should clap for the winners. Yeah.
Yes.
Okay, so yeah, congratulations to all, and I would like to pass on the baton to Dr. Shovan for the final words for ending this conference. Thank you once again for being with me for a long time. So see you again. Bye. Dr. Sovan, please.
Yeah. Thank you. Just a second.
I want to interrupt just after Shobhan's speech. Don't go. We have a photo session, the last photo session of today. So please don't go.
Sure. Yeah. So we have come to an end, and it was something like in 2 days, so many speakers, around 15 speakers, and 8 to 9 poster presentations. And with this, some very different kind of activity we got there. Fine. First of all, this particular thing means suddenly we arranged these things, and it could not be possible without the proper assistance and guidance of so many people. And if I don't take any of their names, if I miss any of their names, please forgive me. First, I would like to thank the directors of SRF and then the editorial board members of SD. And 3 more persons, I didn't take the names of each and every director and editorial board members, scientific committee members, but 3 persons' names I must tell here. One is the person who was continuously inspiring us from behind, Shubhranshu Bose, Shubhranshuda. Secondly, Saurabh Kanti Jana, I didn't see any such person who could work so hard for this kind of conference. Really, I must thank Saurabh. And thereafter it is coming to Shayan. He was also continuously all the technical things he and other after that Shomodip they were taking. Now coming to Dr. Sritama and Dr. Sayan, who took the charge of all the three sessions and the poster session, and yesterday's one session, today's two sessions, plus the poster session. So they handled so nicely all the things. Just each and everything was picture perfect. And secondly, I must say the conclusions where they were drawing, how the time were maintained, all the other sessions other than the poster we couldn't help there. It was beyond our control also once. So everything went so nicely. For that, Sritama and Shayan, I must thank both of you. Then comes the speakers and the contributory poster presenting authorities. So speakers, each and every speaker, starting from Amit Chakraborty, then Mohendra Roy, then yesterday I forgot one or two persons' name, I think. Then Chandrani and yesterday Angshuman, today morning also, now also, each and every speaker. So it was something wonderful thing that we just requested them within a very short notice. Yesterday also I mentioned, today also. And though they each of them are busy with their schedules, but they helped us and they agreed to come out and they just took the stage, and I would say each one of them basically rocked. So I lost my words to thank to all of them. All the judges and all jury members, they helped us to decide the poster awards. And really, as Chitama was telling, once it was the condition that we were not getting the solution, that how to solve, there was tie, and after that also what the difference was going, somewhere half marks. So it was really a tough competition. Though the competitors were less in numbers, but quality was so good that we got it so nicely. Lastly, all the audience, enter registered members, each and everybody, I want to thank each one of you for completion of first international conference on the convergence of interdisciplinary research, and this is going to be setting a trend from today what we are trend setting, so tomorrow, so that this thing can be continued further. Today's speakers, each and everyone about whom Sritama already told, they also made the things so nicely, so quickly they finished, so that the things can be made in time. I thank all of you, and I must say that as Subhranshu told us, that to announce it from the platform of SRF, that if any of you having some concept ideas which can be just utilized to make the proper industry and as well as research and development, that connecting, that bridging, In that case, SRF is ready to assist you with all the way with legal formalities also. Fine. So I must say that we are concluding now, and at the end, as Saurabh told, that we must not leave before he nods, right? So that we will be having the photo session. Fine, Saurabh, it's your turn.
I request you all, please turn on your video so that we can have a photo, all of you.